I could have talked about Bayesian methods, perhaps, but I decided to talk about something else, which is maybe a topic that is a little bit exotic to this audience, but let's see how it goes. So I'm going to talk about generative models, which is another big thing right now for machine learning, and then with a bit of this causality flavor. So I'm going to start by talking something a little bit, well, controversial, but the controversy does not come from me. So around 7 years ago, I mean, some of you might be there, but not. Basically, there is this debate, or whether deep learning is this alchemist approach that we should proceed going on. For example, at that time, the test of the award presentation was given by Ali Rahimi, who wrote a fantastic paper in 2007 about this random feature approximation to kernel methods. Okay, so this paper still has the great impact today. I also still use the techniques from that paper. But then basically the test of the presentation is mostly not about that paper. It's mostly about Ali Rahimi's complaint about deep learning being no theory at all, the alchemist approach. Okay, so I think at that time, after the talk, so he received a very long applause, okay, about his talk, and then it generates some discussion. But then we see Yana composed a blog post right after the talk, basically saying that, okay, so you do need this alchemist approach to move things forward. And okay, so this is 7 years ago, and if you fast forward to nowadays today, I think pretty much Yana was correct. Okay, at that time. So yeah, okay, so this is some complaint from the theoretical people, but then it is a bit true in the sense that indeed we still don't understand why deep learning works, right? And we do a lot of engineering approach, more or less like it's alchemist. Okay. I'm going to also tell you about basically the other end of the spectrum, which is people doing causality, especially for people doing theoretical research. So causality research has been around for quite some time, I think since the 1980s at least. Okay, and you have a bunch of people from the stat community doing causality, and they are being very, very theoretical in the sense that they really want to specify, the assumptions and conditions to show their theory can work. And sometimes they might not care about whether their assumption is realistic or not. They just want to make sure that their theory works. Okay, that's my claim. Okay, and I think on some day of this workshop, someone mentioned to me that the Bayesian community seems to be quite opinion and then fight with each other. I think that's also the same thing happening in the causality community, that people are in different camps and they don't agree with each other's things. But most of the time, they are focusing on really whether their assumptions in theory, right, are correct, and whether you can prove nice theories given your assumptions. Okay, so the interesting thing here is I think most of the traditional causality research, they assume, for example, like linear models and make really unrealistic assumptions saying that you observe all the variables you have, which is not true. Okay, so we notice these things. I mean, a lot of people notice these things and notice the gap, right, between the reality and the theory. And then people also want to make deep learning a little bit less alchemist, maybe get some theory inside that. So you have a bunch of people organizing this new camp called causal representation learning. So maybe during this presentation, you can think about whether you place these people in which part of the spectrum. Okay. Okay, so this is actually going to start my real content. Okay, so I get interested into this problem because basically 6 years ago, I published this paper together with Ehsan Amid, where I interned with him at Disney Research doing video generation. Okay, so this is the state of the art 6 years ago. You need to appreciate that after 6 years, we have a tremendous progress, okay, for the video generation. But this one is not purely just for, naive video generation. The thing we want to achieve at that time was to get this disentangled representation or compositional representation in the sense that I want to separate the representation of starting information and temporal information. So in this particular example, you can think about these, dancing character videos in this way, right? The starting information will basically be like this content or style, or let's say the attribute of the character, and the temporal information will be the action or movement of the character. Okay, so this is the data set. Okay, so we built a model that I will explain in a moment that can achieve this kind of separation of starting information and also the temporal information, so that I can basically generate things by, for example, fixing the starting information and then just varying the temporal information that you can see you can generate the same character doing different actions. Or you can basically fix the actions of the characters and then vary the representation of the starting information so that you can see basically different characters perform the same action. So I should also mention that this is done in a pure unsupervised manner. So this is important to keep in mind for that. So this basically says I don't have any attribute labels. Okay, so I don't use any attribute labels, although I could have, but I didn't use that at that time. Okay, so this is obtained in a purely unsupervised manner. Okay, so the idea is actually quite simple. If you are familiar with generative models or graphical models, then this should be very intuitive, right? So you want to separate the starting information from the dynamic information, then you just build different latent variables to basically separate them, right? So essentially you can see this sequential generative model says, okay, I'm going to use a latent variable f to represent the global information or the starting information, and then I have a sequence of latent variables z1 to zt to represent the dynamic information. Okay, so this is a very intuitive if you are into the design of graphical models. So the rest of the things are just standard recipe for generative models, right? You put in neural networks to parameterize these generative models. In this case, I use LSTMs and CNNs. Okay, and then the training strategy is also very standard. You just do the variational auto-infinite approach. Okay, good. Okay, so this is a simple recipe, and I previously showed you that it works in this unsupervised learning setup. We indeed make it successful. Otherwise, we wouldn't be able to publish this paper. Okay, but the interesting question here is, would this strategy always work? Okay. So the funny thing here is no. Okay, I'm going to tell you that powerful neural networks can cheat, even within this model design. Okay, so the use of LSTM is key here. Okay, so previously I told you that I want to use these F variables to represent global information. I want to use Z1 to ZT to represent the dynamic information, but there is no guarantee. The LSTM can cheat in the following two ways. So, for example, you remember that in LSTM you have this, hidden cell states, also within its architecture. Okay, so this basically means it is possible for LSTM to learn how to actually copy the internal state, right? So, if it can actually copy the internal state, then essentially you can start by capturing, let's say, the content information in the first initial hidden state, and then just copy it forward. Okay, so this tells you ZT can potentially capture the content information. Okay, so this is one way that LSTM can cheat. Another way that LSTM can cheat is basically related to actually the underlying ground truth. Okay, so this data sequence inherently has a deterministic dynamic model. Okay, and if you think about deterministic dynamics, right? So to a certain degree, once you know the initial condition, then you just simulate, let's say, your deterministic dynamic model, and then it will just give you the entire sequence. Okay, so this means if your F variable actually learn both, let's say, the content information as well as the initial condition of, let's say, that particular action sequence, then it is possible that F, also capture the movement information, and it just, carried away to get the final sequence here. I think basically the lesson that I learned from doing this project, okay, in hindsight, is basically that if someone shows you a graphical model design, telling you that, okay, my design here has this promise that, okay, this variable will capture this information, that variable will capture that information. You might actually need to take it with a pinch of salt. Because if you don't actually talk about how you parameterize those errors, then neural network can cheat in various different ways, as I just showed you. Okay, so I realized this after I published this paper. I need to say that I'm not criticizing my previous own approach. Okay, so yeah, let's just try to go a little bit deeper to really understand where the problem comes from. Okay, so we can go back to, well, anyway, I just say that my solution at that time was alchemy, okay, tuning hyperparameters. Okay, so the real problem comes from the issue of identifiability. So let's just go in that a little bit deeper, going back to this static case, and this case is presented in this best paper at ICML 2019. So imagine you have a generator that can generate nice-looking tomcat. Okay, so basically, this generator would take a noise variable Z, run a Gaussian distribution, go through a very complicated process, and generate an image. Now, imagine there exists another generator which, somehow the latent variable is rotated using some kind of rotation matrix. So if your neural network is powerful enough, right, then the neural network can, for example, first learn how to rotate back the latent representation, and then learn the subsequent function as basically the previous G function. Okay, and you can still see you have the same generation result. Okay, so this is really the problem of non-identifiability. It basically says, for many of the latent variable models or deep generative models, right? If you only look at how the things are generated, or let's say the distribution of the generated data, you have no guarantee to tell you what kind of neural network architecture you've learned, what kind of representation you've learned. I've just shown you there are two equivalent models, right? That basically generate exactly the same kind of images. Okay, so yeah, you can really not tell the guarantee in terms of, say, the structure of the representations you learn. Although maybe authorization will give you some bias, I'm just purely talking about the possibilities of having two equivalent generative models. Okay, so yeah, so identifiability is actually a very important concept, even just in traditional statistics. Okay, so I'm going to go through the definition, and then if you do have questions, then you should ask right now, because this is actually very important for the rest of the talk. Okay, so I mean, there are different ways to work on causal discovery. Okay, one way is called functional causal models, which means I'm going to make some assumption about the relationship between my variables using a framework called structural causal model or structural equation model. Okay, so for example, in, let's say, regression or classification setup or regression setup. Okay, so you're going to say my target variable y is a function of my feature variable or input variable x plus some noise. Okay, so this definitely defines a probability distribution that is the model P of theta of y given x, right? Okay, now in terms of identifiability, we haven't talked about learning yet, okay, but just in terms of identifiability, we are asking the question that whether the statement that two distributions within this model family are equal is the equivalent statement about, let's say, the parameters that are equivalent. I'm not saying equal, I'm saying equivalent. We need to talk about this equivalent definition in a moment, but one example you can think about it is basically mixture of Gaussians, right? Mixture of Gaussians, they are identifiable basically up to the permutation of your component. So this is where this equivalence comes from. You cannot get exact equality in most of the cases. Okay, so why this is important? Okay, so the reason why you want identifiability is the following. So, most of the time we make model assumptions, right, of the underlying data we want to model. So if you have no model error, which is a very big if, Then identifiability is basically asking you the question that, okay, if I have no model error, I have enough amount of data, whether I can recover the ground truth from the data. Okay, so well, if you don't have identifiability, then I think you might not need to even worry about whether your model assumption is correct or not. Okay, so that is not meaningful. Anyway, so many of the traditional statistical models, they have identifiability. For example, like this, regression based models, and some simple latent variable models like mixture of Gaussians. They have proof identifiability, and people on top of this result prove estimation error and consistency results. Okay, but anyway, so once you have identifiability, then you can basically fit your assumed model to data and then check whether your model fit is good, right? If you have a good model fit, then you can basically use your fitted model to answer many of the causal questions you want to answer, for example, like intervention or countervention reasoning. Okay, so I hope this setup is clear, but then let's just see what is the, okay, yes.
Sorry, just maybe a very dumb question. What exactly is the definition of identifiability?
Okay, it's basically this line, yeah.
Because here, what you show here, actually, you always define, like the equivalence of weights from the other way around. You say that, oh, whenever this is true, these weights are equivalent. In this case,
no.
It's like always
okay.
identifiable.
So this is the definition of the identifiability. You need to check this condition. So it is not always true that any model will satisfy this.
Yes, it's just like somehow because identifiability is something that you need to define, and then like the equivalence between weight is also something that you need to define. And then it's somehow like if you can't fix anything like one of these results using the other one, then it's kind of like
yes. Okay, I see. Okay, I see your question.
Yeah.
I think you are right that you need to first describe the kind of equivalence that you can accept. Okay. So it's in some sense like if you think about neural networks, right? So the question here is basically, okay, whether you are happy with, let's say, learn any possible neural network weights, or you want your neural network weights to have some kind of structure. Okay, this some kind of structure is the kind of equivalence that you can accept. Okay, I mean, if you don't define any kind of equivalence constraint, right, then you don't really care about, okay, whether you get back to some kind of meaningful weights as long as the distribution match.
Maybe you're going to get to this, but I guess sort of your argument goes like, neural networks are non-linear, so they have multiple solutions that will give you zero error. So there's many thetas because of all of the symmetries that will give you the same function, so I cannot identify it. But I feel like it's more of a question of granularity. Like some of these things don't matter. Sure, I can permute some hidden units between them and I get the same function. They shouldn't change. There's a higher level structure where you want to say, okay, there are these bottlenecks, and at this bottleneck I'm only representing this and that bottleneck, and I feel like that shouldn't be that hard to enforce. I mean, we need to enforce it manually, but I think it's really doable.
You are predicting the next slide.
Oh.
Okay. Yeah, okay, so as Razvan has already kind of somehow predicted, right? So we in neural network worlds, right, we don't care about exactly the structure in the weights, but we care about structure in representations, okay? So basically you can see that this slide and the previous slide are basically the same, except that you're going to change your model assumption and also, let's say, the identifiability criteria. Okay, so instead of working with basically fully observed case, I'm going to assume that you have a latent variable z, okay, and your data x comes from basically this interesting neural network function mapping from z, right? So the one thing that is different from previous setup is now you don't have fully observed case, right? So you never observe latent variables. So this means when you check identifiability, you have no way to also check the distribution of z. I mean, going back to our previous Tom-type example, right? You can only check the distribution on x, your generative data, okay? So now identifiability here basically says, okay, if I have two generative models under the same model class assumption that gives back the same distribution of, let's say, the images, okay, I want to say something about whether, let's say, they are learned function mapping, which relates to the representation, have some equivalence relationship. Okay, so this is the identifiability that you want to study here. Okay. So I mean, once you can somehow establish some kind of identifiability, you do the rest of the things, right? That is the same workflow as in the previous case. Okay, so I'm going to talk about basically how we do that in the context of a time series or sequential data. Okay, so the nice thing about sequential data is basically you don't need to worry about defining the direction of the arrow in this causal relationship, right? Because you have the arrow of time. So we are not worrying about orienting the edges for those people who actually know causality. Okay, but the other big challenge in sequential data is basically how do we actually model non-stationarity. Stationarity data is not very interesting, and we know many of the real-world sequence data, they are non-stationary, right? So you have people working on stationarity cases. There are actually tons of people working on this non-stationary case based on different assumptions. So we also work on that. And so this is the paper that I'm going to present that will also be presented basically a month after this workshop at ICML. Okay. So the motivating example is we are going to work on switching dynamic models coming from this motivation of this salsa video. So my student is Spanish. He really enjoys salsa dancing. Okay, so you can have non-stationary behavior in your sequence. And then our assumption here is the non-stationary behavior comes from what is called regime switching. Okay, so it's basically like, in salsa dancing, you have the dancers, they are going to basically perform in a very different way when they are in, let's say, different, section of the dance performance. Okay, so we are basically saying that, within the same regime, the or condition on the same regime, the dynamic itself can be stationary, but it is due to non-stationary switching between the regimes that you have overall a non-stationary observation sequence. Okay, so this is our assumption. Okay, I hope this is clear.
So it's stationary within the regime.
Yes.
And then switching this cause.
Yes. Although we don't actually know the non-stationary switching pattern. Okay. So the kind of model that we are going to work on is we start from this model called Markov switching models. I mean, it's a bit like hidden Markov model, okay, except that you also have the connections between the observation state, okay? So there are something to note here, right? So if you remove, let's say, these arrows, it's just a hidden Markov model to something. And also, as I previously said, right? So the discrete switching states can be non-stationary, right? So we don't actually specify, let's say, first order dependencies. We basically say, okay, it could have, let's say, higher order dependencies or have some interesting non-stationary behavior. The only assumption that we are making here is condition on the regime state ST. Okay, my observation sequence is going to follow a first order Markov model which is stationary. This is our only assumption. At least for now. Okay. So now you actually start to ask the question, okay, so when is this model identifiable with observations of the sequence only? So remember that we never observed the switch or the segment label, okay? So now you should be skeptical, right? Remember at the very beginning, I just tell you that if people somehow tell you that I give you this graph and I tell you some kind of identifiability guarantee, right, then it is wrong. You need to really talk about how you parameterize those arrows in order to say something about identifiability. So now we are going to say something about those arrows. Okay, so this is basically the informal results. That is a big replacement of the actual result we proved. Okay, so we basically said that this model is identifiable up to state permutation. Okay, we are happy with permutation of the state. Okay, when you satisfy these two conditions. So the first condition basically says that you need unique indexing. So in other words, it basically says that there won't be two different indexes that says if the underlying dancing pattern is the same. Okay, you need to use different index to denote different bouncing patterns. So this is what unique indexing is saying. So the second condition basically says, okay, I need to parameterize, let's say, these arrows, right, with neural networks or whatever other, say, parametric family. Okay, so if you're going to use a Gaussian distribution to parameterize these arrows, okay, then you need to make sure the mean function and the covariance function as a function of the previous time steps observation x t minus 1 is smooth, okay, in xt minus 1. So this is the condition we are saying. Okay, so this condition is actually not that bad. Okay, so it tells you that, I mean, you don't even need to talk about architecture of the neural network. You just make sure that this neural network parameterizes a smooth function. Okay, so for example, you can use soft plus, sigmoid. Okay, those are smooth activation functions. As long as you use them, they are fine. Okay, ReLU is quite tricky. We don't recommend using ReLU. Okay, so the intuition is actually quite simple in the sense that if you have these continuities, right, in your sequence, you want the switches to represent these continuities. Right? If you have some way to represent these continuities in the within, let's say, this continuous distribution, right? Then somehow, the discrete states can be redundant. Okay, so this is essentially the maybe the rough intuition behind that. Yeah.
It makes sense. I was wondering if they're like in practice, you need them to be sufficiently different. It's like strong complexity. Do you think that they need to be far enough? Show up.
Okay,
it's
that
not equal, I understand, and then that leads to a very simple condition.
That doesn't show up. I will show you the proof strategy and tell you why. I don't think you need strong complexity. Although it could maybe help in learning, I guess.
No, like I was saying, convexity versus strong convexity. Like you could say convexity, but then strong convexity is much nicer. That it has some.
But I guess convexity does not is not excluding non-smooth function, right?
You can exclude the comment about convexity because I mean exact non-equality. Like you need them to be just not equal, but also different, like sufficiently different.
Okay, I can show you how we need some kind of sufficient difference. I will show you. Okay. Okay. So let's think about how we actually prove these things. Okay. So it's a little bit involved, but the logic should be fairly straightforward. Okay. So the funny thing here is you can actually think about this very complicated first-looking model as a mixture model. Okay. So think about Gaussian mixture models, right? You are indexing the Gaussian components with only, let's say, one variable. But now we are going to index the mixture components with what we call path indexing. Okay, we are going to index the components, basically this P of the X entire sequence, given, let's say, the entire sequence of the switches, right, as one component, and then basically your component is indexed by the entire sequence. Okay. So once you agree with this finite mixture model view, then the rest of the proof basically just comes from checking basically the conditions that needs to satisfy for identifiability in mixture models. Okay, so let's see how it works. Okay, so first, identifiability for finite mixture models require linear independence of the component family. Let me say a bit about linear independence. Okay, so it's basically saying that, okay, if you have a function family, right, that contains linear independent function, right, then basically the functions in this family, right, can form a basis of some function space. Okay, so this is what linear independence means. So roughly, it says that you want basically your distribution family there to basically form a basis in some function space. Okay, so this is the first step coming from the identifiability for mixture models, finite mixture models. Okay, so the second step is we are going to exploit the assumption of first order Markov structure condition on the states. So this allows you to factorize the big component distribution into a product of basically these first order Markov transition distributions. Okay, so this essentially gives us some hope in terms of doing proof by induction. Okay, so we are going to start to see, okay, whether we can actually show this first step for basically the first two time indexes, x1 to 2, okay, and then we can see whether we can prove these things by induction. Okay, so this is the second step. The third step is actually the most involved one. We spent a tremendous amount of time doing this. I can tell you a bit about why this is difficult, okay? So, but at the end of the day, we actually work out some condition in a non-parametric sense, okay? About, okay, how to actually impose conditions on the this first order transition distribution so that the product distribution is actually linearly independent. Okay, so the last case is basically now we are going to go for the generative model or the parametric case, right? Say, okay, now I have parameterized this distribution as a Gaussian distribution with some mean and some covariance matrix. What kind of conditions should this mean function and the covariance function satisfy so that I can make them satisfy the third step conditions I have? Okay, so it turns out that you just need to make sure that they are smooth in the previous time step inputs. That's fine. Okay, so that's a little bit involved, but I'm going to tell you why Gaussians are nice in this case. Okay, so it's actually about this smoothness of the functions in this. Okay, so imagine you are thinking about basically two Gaussian densities, right? If these two Gaussian densities overlap at some interval, they must be equal everywhere else. Okay, so basically, if you have two Gaussian densities, right? I'm saying that, so this is one Gaussian density. If I'm going to, let's say, draw within this interval another Gaussian density, right, and we actually somehow overlap basically on top of each other, exactly the same, right? Then you can actually predict that in all these outside region, they must be equal. That's basically the property of Gaussian. There is no way that you can, let's say, do this. No. Okay, so you can imagine yourself, okay? So, yeah, so this is the nice thing about Gaussians.
So, sorry, I have a good question because previous slide. So here, x1 sub 1b is just a point or this is a random variable. So because you consider the linear independence of the family, so this means that the linear independence of a family of functions or just values.
Over functions.
Okay, so x1.
So imagine P here is a function of x1 to t.
So this is just a vector or random variables. X is just a vector in some space.
Yes.
Or this is not random variables.
In this case, we are not proving things on random variables. So you just imagine this is a function. Yeah, imagine this is a function of x1 to t. We are just trying to show that this set of functions is some kind of, say, basis of some function space. Yeah, you don't need to fix x1 to t.
Okay. Then so the index is just t.
Well, the index is not just t. If you have a function, right, x1 to t is the function input. Okay, this state s1 to t, you can think about it as the index of the function to a certain degree. Okay. Okay, so we just talked about what is nice about Gaussians, which is why we choose Gaussians. But then why do we actually choose analytic functions? Okay, this might actually relate to Anti's question about some kind of sufficiently nice properties. Okay, if you have a infinitely smooth function, which is essentially just analytic function, right? Then you know that these two functions in this infinitely smooth family can only intersect at finite, or not finite, basically a zero measure set of points. Okay, there is no way that you can have, say, intersections that looks like. Okay, so if you have this case, so this is 1, 1. Okay, analytic functions won't have this case.
So when you talk about infinite smooth functions, what condition that this brings you on the covariance? Yeah, this infinite smooth functions, you said it, yeah, this corresponds to more or less a Gaussian covariance.
Yes, I'm going to talk about it next. Okay, so I can tell you why we want this. Okay, so I talked about some nice thing about Gaussians. I talked about some nice thing about these smooth functions. If you combine them together, okay, then it basically tells you that this Gaussian function, I'm not going to talk about distribution, Gaussian function as a function of both xt and xt minus 1, okay, can only sort of like intersect as some zero measure set. Okay, so this is actually a key result. The reason is the following. So if you have, let's say, two functions, this kind of function that can only intersect at two at zero measure set, then it means that, you know, in reality, with probability 1, you will observe some differences. Okay, so it basically tells you that with probability 1, okay, then once you see, let's say, these two things being equal, then you have the mean function and the covariance function being equal.
Hello, sorry. Oh, can I ask a question? Okay, sorry. I'm going to be like the mean engineer.
Yeah, okay.
Always work against mathematicians. So here, of course, I mean, from a mathematical point of view, zero, like equality is nice. But if you actually going to implement this, like especially using, you know, deep learning framework or whatever, you are dealing with like floating point arithmetics that is never equal. And then there's always like, you know, like people say they are like close enough, right? You can only say this. I'm just wondering if your proof can somehow kind of have this kind of saying that, oh, if they are close enough, this still holds, or like if you have like a non-zero gap, then you can overprove it. Or I don't know if this.
I guess your question here will then relate to how much overlap you can allow, right? So the main thing here is the following, right? So in some sense, this gap, it describes, let's say, the error margin that you can maintain or you can accept. So in your kind of engineering kind of problem where, let's say, if the error is, let's say, e minus 6, then you say they are equal, right? It means that you have some kind of interval, right, that you can accept them to be overlapping. So I guess this basically says, okay, in addition, I mean, maybe you can relax this condition from basic analytic function to maybe less smooth, but you need to talk about something about, let's say, this smoothness again to accommodate, let's say, this error interval. Okay, but I agree with you, right, that this is a purely, I have to talk about nothing about learning. Okay, I'm not going to talk about learning today. Okay, so, yeah, but before we talk about the discussion about, let's say, what is why this theory is interesting, maybe we can see some examples. Okay, so I motivate the task with these dancing videos, right? So we are going to start from an easier setup, which means I have, let's say, the key point tracking data or for some salsa dancing video. Okay, I want to use some generative models to understand this sequence, for example, like segmented sequence. Okay, so we tried basically the model following our previous assumptions as well as a deep learning baseline, which is called common BAE. Okay, so I think the interesting thing here is that, okay, so it works decently okay, right? That depending on which states this dancing sequence is in, you can basically see different kind of behavior. For example, like this forward, backward kind of a movement, turning around and double spin this thing. Okay, so yeah, so it shows that the previous model assumptions, right? They are not sort of like too restrictive. I mean, you can still make it work in the real world data setting. Okay, but this is not real world enough. I will talk about it a little bit more real world setting. Okay, so I want to discuss a little bit about basically the theory. Okay, So first, this is actually a quite different result compared to basically the identifiability result in hidden Markov models that was published basically like 15 years ago by well, the second paper. Okay, so the main problem in terms of the difficulty is actually this overlap here. Okay, so if you remember in hidden Markov model, right, there is no arrow. Okay, here, which means you will have basically multiplying two, independent distributions. So I can tell you one example why proving proving independence is so difficult here. Okay, so you imagine you have a family of functions, let's say on x and y. Okay, and some family on y and z. Okay, so if you have this state equals to, let's say, x, y, x squared y, x cube y, or something like that. Let me see. Maybe it should be the other way around. X, y. Okay, you clearly see that this is a family of linearly independent functions. Okay, but you can set up something very funny. Okay, let's do this. Okay, then if you multiply these two functions, which is exactly what we are doing, right, in the conditional distribution product case, right, then you will have some kind of, let's say, x, y squared z, right, x, y, okay, I'm doing these two things, right, but if you also multiply, let's say, these two things together, then you result in the same functions, okay, which will produce redundancy. So this is the reason why when you have overlapping variables here, naive assumptions on your conditional distribution does not lead to linear independence when you multiply them together. Okay, so we spend tremendous amount of time to basically eliminate these kind of problematic cases. So that's basically why you need some kind of smoothing conditions. Okay, so the other funny thing about this, which is actually quite nice in terms of non-stationarity cases, is because we are treating this model as a giant mixture model, right? We make no assumption at all in terms of the discrete state transition distributions. Okay, so the results can identify both, let's say, the conditional distribution as well as the joint distribution of the states. I mean, once you can identify this joint distribution, then you can basically work out all the conditionals, right? So this basically means you can actually have a non-stationary and high-order Markov model for basically your state transitions, discrete state transitions, and then once you marginalize out the discrete states, then the marginal distribution over your observations can also be non-stationary and high-order Markov. Okay, I think this is a pretty interesting result.
It must be high-order Markov. Not that it can be, it must be. When you marginalize out the latent.
Yeah.
Yeah, you said can be, it must be.
Okay, must be. Okay, so you can also extend this result to include some other external variables to conditional on, right? So, I mean, as long as, let's say, your external sort of control signals, they are constructed in this way, I mean, the proof will just directly work out. Okay, so the previous example is somewhat interesting in terms of theory and a bit of experiment, but going back to our previous problem, right, what we really want to address is the deep learning setup, right? So previously, the example is basically key point tracking sequence. We want to see whether we can actually do these things on videos. Okay, so this basically means you want to actually lift the dynamic model to the latent space, and then somehow use some kind of a deep neural network decoder to convert the latent representation to the frames. So this is the model that we are going to look at, right? So the previous kind of switching dynamic model, the MSN, is basically limited to the latent space. And then you're going to have a neural network-based decoder to really generate the video frames, okay? So you can ask a similar question about, okay, can I say anything about, let's say, identifiability guarantees on this kind of model? Okay, it turns out that you can, okay? So we are actually leveraging a previous work's result I will mention in a moment, okay? The informal result says that this, okay? So first you want to make sure that, let's say, our dynamic latent prior basically looks like the previous identifiable Markov switching model, okay? The other thing is actually talking about these emission distribution, okay? So the emission distribution here, if you look at this one, it's going to be a Gaussian, okay, with some mean parameterized by a neural network and basically a covariance, a noise term here with a constant covariance that you define, okay? So yeah, then you need to talk about basically the function itself, okay? You cannot talk about any function. Okay, so this decoder function needs to be continuous and injective. Well, injective basically means that it's like one-to-one, okay? I mean, I think you can get a weaker identifiability result if you relax the conditions, but that's a little bit too much. But essentially, I think this says it allows us to use certain kind of leaky random networks, okay, for these errors. You still need to use smooth functions or smooth neural networks for those errors here, but you can use a certain kind of leaky random networks for these errors. Okay, so the proof actually does not come from us. We are basically just using or reuse some previous papers results from basically this newest 2022 paper. So their idea is basically there is a line of research trying to show identifiability of VAEs. And in the previous results, people show some identifiability of VAEs with some assumptions, but then they need, let's say, some external auxiliary signal to pin down the latent variables. So this paper says, no, you don't need that. As long as your prior distribution over your latent variable Z is an identifiable finite mixture. Okay, so remember that previously when we do this sequential case, we have already proved basically this latent dynamic model as a identifiable finite mixture model, although it is a mixture of exponential number of components. Okay, so then basically we just reuse the previous result by grouping all the mappings into a giant mapping. Okay, and then check basically what are the conditions you need to satisfy for these small f's in order to make sure that this big F satisfy the conditions in the previous paper. So this is essentially what we did. Okay, so let's see some results. Okay, so this is a semi-realistic example. Okay, so the with the previous key tracking sequence, we can actually render some 3D videos, right? To actually have a video sequence as input. Okay, so the first thing I want to say here is basically, I mean, this model in terms of the modeling power is not that bad. Okay, so you can still reconstruct, let's say, the ground truth sequence in a pretty good quality. Okay, so you can actually apply these things to segmentation problems. Okay, I think these lines are not very lined up. Maybe the distribution here is not that great, but essentially, I think the point here is we are trying to apply basically this method to do segmentation to see whether we can discover interesting dancing patterns. Okay, well, at least you have some very interesting dancing patterns that here, right? That is clearly different from the dancing patterns here. Okay, so this is a semi-realistic setup. A more realistic setup here is really coming from a real-world dancing dataset. Some Berkeley people collected a dancing dataset by asking a few dancers to basically dance in different hip-hop dancing style. Okay, so we basically apply this model to these real-world dancing video sequences. Okay, I think in terms of reconstruction, it seems okay, although you have similar problems with VAEs in terms of the sharpness of the reconstructed images. Okay, but in terms of the segmentation, okay, it has found some interesting pattern. Okay, so you can guess what is the actual pattern here. Well, the funny pattern that it actually found is basically the movement of the dancer from the left to the right. Okay, so I would say that, you know, it can find something, but again, right, this basically goes back to the some of the questions that we talked about in the very beginning, right? So identifiability here will really help where you have no model error in terms of assumptions. Okay, so this is the thing that is really difficult to test. So usually what you know, the causal representation learning people can hope for is basically, you know, showing some identifiability guarantees and then hope in the real world data testing, okay, their model assumption is close to what is happening in their data. Okay, so we have some work in progress. I mean, clearly, people want to also work with higher order Markov transitions, and this will actually make more sense in data, in analyzing sequence data from, let's say, neuroscience and climate data. And another thing that I think is actually more important is to include the observation dependent state transitions. I mean, the previous model, right, if you remove the red edges, basically says that the latent discrete state transition is autonomous. Right, the real world kind of say like observations has nothing to do with the latent state transition, so this, which is not related. Okay, we really want to add in these arrows, and when you actually add in these arrows, you can no longer treat this model as a giant finite mixture model. That is very hard. So you need to start making some assumptions in terms of these arrows and these arrows, and we have some theoretical results already when you assume first order Markov transitions on these latent states. Okay, so I mean, you also want some other assumptions of these decoder function f. Injective is not very nice, I have to say. The third thing, which is can be very interesting, is to prove these things beyond time series. Basically, the magical step, which is trying to resolve this pathology case, right, does not use, at least in our proof, we do not use any, you know, specific properties in time series. Okay. So I think I'm finishing, okay, but I just want to highlight the last point, right? So in this talk, I mainly talk about identifiability, right? So those are all, in some sense, math games, okay? I talk about nothing about learning, okay, which is actually one of the biggest problems or one of the biggest challenges right now within the field of causal representation learning. Okay, so first, as I said, right, you usually you don't have this luxury of, let's say, no model error. Always, okay? And the other thing here is actually about learning. So these latent variable models, right, you cannot fit it with exact maximum likelihood. You need to do approximate inference. And whenever you start to do approximate inference, many of the guarantees in terms of consistency and, let's say, this asymptotic behavior in the previous proof can break. Okay, and I want to mention that in sequence models, actually a simple version of autoencoders can be quite tricky to tune to make it work. Okay, you obviously need some more advanced methods. But then the other interesting question here is, does this kind of research really matters in this kind of, say, let's say, deep learning regime, right? So I just want to highlight to you, right, these things that you have all seen, right? So this is stunning. I don't need to tell you how good it is, okay? But I want to mention the interesting thing here, which is the model they use underlying, right? So they are using this, diffusion vision transformer thing, okay? So the techniques they are using here is they are going to cut, the video into these space-time patches, right? And then model them as basically a sequence, depending on how you sort of like rasterize these things. And if you use transformers, I think in practice you are not really doing, let's say, this the sequential processing. You are just parallelizing all, okay? which basically says, I don't think they are sort of like explicitly enforcing these kind of say error of time, okay, in the modeling procedure, where this error of time is a very key concept in what I said about the causal representative learning, right, in the time series setting. Okay, so the interesting question here is, okay, can you say anything about causality, right, or causal representations when both of the people right now in this video generation industry is looking at these kind of models? Okay, we can talk about this offline, but I just want to end with this note, right? That I think we should definitely use the deep learning models to basically, leverage their power to learn low-level representations, and hopefully those representations are like perceptual features that basically give us some kind of say high-level representations. Okay. And one thing that might be interesting to think about here is people are not interested in this causal relationship between pixels. They are interested in, let's say, the relationship between objects, and for objects, you need these representations, right? So once you've got these, say, perception representations, right, then you can apply maybe your favorite causal models. And essentially how to build those kind of, say, perception representations, and how are you going to build, let's say, causal models on top of that. I think this is basically the scientific alchemy. Okay, you figure out the theoretical limits, and then you leave the rest to perception. Thank you.
Thank you. I must say, I didn't understand the word causal in this sense. In this setting, how you kind of think about causal. It's just that it depends on previous, whatever happens now depends on the previous time.
Okay.
Because normally the use of the C word in this kind of setting is, we have to be very, very, it's a very loaded word, So if you only mean what happened now depends on the past, I don't understand the use of causal in this.
Okay, I can say something about this. I think what I presented here is actually something even before we do something on this causal inference, or let's say doing interventions or counterfactual inference reasoning, right? But I think the interesting thing here is you need to actually first show identifiability, right? To actually show that, okay, you can trust your model to learn some structure before you can actually manipulate your model after you've learned it. So to some degree, today the papers I'm presenting here is basically kind of like a one step, basically before we actually do the interesting causal thing. I understand this causal word is very overloaded. Okay, but I promise you, right, that people do want to use these kind of models to do the later interesting things.
And maybe just like a follow-up to Laura's questions. And could I just summarize what you just said by saying that basically this kind of question of identifiability, you are still kind of considering this in the level of correlation, like probabilistic graphical model, and not yet like the causal part. That's not kicking yet, right?
Let's say in this way, I think identifiability is a concept that is even beyond causality, right? So for many of the statistical models, you can also talk about identifiability. Now, the interesting question here is for causality people, right? They want to build structured models, right? So that if they can get those kind of structures, they can actually start playing around with these causality things. We are answering basically the prerequisite question for them, right? If I build a model that's somehow supposed to have some kind of structure that implies some kind of interesting you can play with later on causality things, right? Where they can actually get that structure back from data in the first place. Okay, we are answering that in some sense the prerequisite question.
Okay, but maybe this question is kind of like can be answerable like just from considering like independence and like correlation, or you think that this really like causal thing should really kick in at some point to really solve this identifiability problem?
Well, you have a lot of different ways for people to actually answer this question. Okay, so for some people doing causal discovery, right, you can actually do something called conditional independence test. Okay, to actually discover the graph. Okay, for example, you can determine whether, let's say, in the graph, two nodes are really connected to each other or not. Okay.
Sorry, but this is actually like still like in like probabilistic graphical model level, right? It's like something that you receive in callers would like how to identify like how to do the test whether like these things are connected or not, and whether like it makes sense to actually have like the direction or like both directions make sense.
Yeah, I mean, I think this, okay, so I think I see what you mean. So this discovery part is to some degree, right, still within this realm of probabilistic graph models. What I'm trying to say here is I'm presenting to you basically this prerequisite step. Once you get that, right, later on when you do interventions or counterfactuals, then you need to somehow go beyond the usual kind of inference rules in probabilistic graph models. Okay, it's when you use it, then it starts to be different. But purely just for, let's say, discovering the structure, okay, I mean, if you don't use it, right, then probably it won't be that different. I want to answer your comments in the sense that it can detect basically the graph structure up to some equivalence.
Yeah, then you just define it, yeah.
Yeah, you need to define equivalence.
No, it's fine.
Identifiability is all about defining acceptable equivalence. All right, thank you very much.
Thank you for the introduction, and also thank you for the for giving me this opportunity to talk here. In my initial plan, I was going to talk about my recent work on learning transfer, but during this workshop, I realized my other previous works is also match the interest in this workshop, so I changed the title to include them. Today, I will talk about these two topics. The first one is a brain-inspired learning algorithm, which is actually not biologically plausible one, but rather mathematically plausible methods based on low-etiquette hypothesis. And the second topic is the new problem of what I call learning transfer, which is something like dual notion of transfer learning in some sense. Okay, so let's start with this first topic, which consists of two papers. Okay, and the initial motivation of these two papers is a learning mechanism in our brain. I'm not familiar with neuroscience things, so this slide is an informal one. Okay, and recent studies in neuroscience shows the structural plasticity plays a key role in learning a new behavior. Structural plasticity means synaptic rewiring between neurons. So, and this is the illustration of the structural plasticity. It prunes and grows the connections between neurons without changing the total number of connections in our brain. And also it may occur more frequently depending on changes in our environment or our development stage. So based on this pruning and regrowth phenomenon, we can consider as a one opinion, we can consider deep neural networks should also first learn by structural plasticity and then quickly adapt to similar tasks by synaptic plasticity. This synaptic plasticity is another mechanism in our brain to learn new behavior to adjust the strength of synapses for quick adaptation. And this was my original motivation, but I want to discuss in more mathematical way. So I explain another background of rotate-etiquette hypothesis. The story starts from the seminal paper by Frankel and Calvin in 2018. They claim that, empirical claims that in randomly initialized neural networks, there exists sparse subnetworks, which is called rotate-etiquette, which can achieve good accuracy after training. So this is a procedure to find the rotate-etiquette. First, we sample the initial parameter theta 0 from some initial parameter distribution and set M0 to be all one vector of the same dimension as the theta 0. And then we optimize theta 0 in standard way until convergence, and we get theta star, which is optimal parameter. And we prune theta star and prune the smallest weights in theta star, and we get binary mask M with M1. And back to the initialization and set M, use this M1 and optimize the subnetwork corresponding to M1 and iterate this procedure. Then we get the rotate-etiquette. But actually, this holds, unfortunately, only when the neural network is small scale, like resonate with 10 layers. So, but later on, about 1 year or 2 years, Ramanujan et al. Empirically showed another phenomenon called strong rotate-etiquette hypothesis. They claimed in randomly initialized neural network, there is sparse subnetworks that can achieve good accuracy even before training. And surprisingly, this holds even when the neural network is larger, like resonate with 100 layers. And also the procedure to find strong rotate-etiquette is very simple. First, we sample the initial parameter theta 0, and we optimize the binary discrete mask M by straight-through estimator, which enables us to optimize M but in a continuous way, continuous optimization by using proxy parameter called score parameter, which is a continuous variable. And then we get the strong rotate-etiquette in this randomly initialized neural network.
Sorry.
Yeah.
So what are you optimizing with? Like, there's no data?
There is data. So, on C10 or MNIST.
So you learn a binary neural network. Is that what you do?
So, what means the
Randomly initializer exists even before training. So I was thinking of finding the mask before training. No?
No. Actually, M should be trained, but theta 0 not require the training.
So theta 0 is fixed, and then you train M
Yeah.
on the data
Yeah.
to find the mask.
Yeah.
Theta 0, which is randomly initialized.
Yeah, so M is actually trained. Thank you. And this is the strong rotate-etiquette. And I explain a theoretical perspective of strong rotate-etiquette. The follow-up works by these ones mathematically formulated and proved the existence of strong rotate-etiquette. And it is something like teacher-student setting, and it is shown that when any dense target network fx is given, then we can find then when a randomly initialized and logarithmically wider neural network G is given, then it contains a subnetwork G, subnetwork by representing by M that approximates F with high probability with respect to the randomness of the initialization. So strong rotated etiquette is no longer a hypothesis. And this is a logarithmically wider network. So we can view strong rotated etiquette as a training method by weight pruning, possibly alternative to the standard training method by weight optimization, which directly optimize theta. But in strong rotated etiquette, we optimize a discrete M. The pros of this method is, one pros is we can use any distribution for weights, which is possibly discrete, such as the uniform distribution over the set of 1 and -1. So in this case, we have a ternary weighted neural network. Okay. But the cons is obviously the logarithmically wider neural network is required. So this method is more memory intensive. These are the background of, okay. These are the background of these two papers. And here we can state the purpose of these two papers. The first paper is avoids the logarithmic factor as the previous logarithmic wider one by pruning and rigorous approach inspired by the structural plasticity. And the second paper is meta-learning of the connectivity structure for quick adaptation, which combines ideas of structural plasticity and synaptic plasticity. So let's start with the first paper, and this paper is titled as Pruning Random Initialized Neural Networks with Iterative Randomization. This may sound a bit weird, but this is actually my first paper in machine learning. So, but luckily, this is also my first spotlight paper in UX. So I was so lucky at that time. But anyway, the idea is very, very simple. I call it iterative randomization. The problem of strong rotated etiquette was the limited approximation capability with a given number of parameters. So we hypothesized that by randomizing the unnecessary weights during the weight pruning optimization, we can virtually increase the number of network parameters. So this is a very simple idea. And the procedure is also simple and very lightweight. This is almost same as the previous procedure of strong rotated etiquette, except that we replace the pruned weights during the weight pruning by random values at every epoch or some iterations. And the pruned weights can be discrete by this theta dot 1 minus m. So we can implement this by a simple formula like this one.
What is D param?
D param is any distribution like uniform, normal, or discrete distribution. Thanks. And this random values is also the same from the same distribution. And we consider several randomization strategies to stabilize the effects of the randomization. The first one is the naive randomization, which replaces all pruned weights by the random values. And more stable one is the partial randomization, which replaces the randomly chosen subset of the pruned weights, which is chosen by Bernoulli variable. And we can control the stability by the hyperparameter R of the Bernoulli distribution. And also we consider a Gaussian randomization in case of the distribution of the parameter is a Gaussian distribution. In case it can be additive randomization, so we expect to be more stable, but actually the partial randomization was enough in our experiments, so I skipped this technique. In summary, these randomized strategies converges to the same distribution if we ignore the dependence in the binary mass M, which is an intuitive explanation.
Okay, I'm looking at this naive randomization, and does that, okay, do you really need the partial one? So the naive one cannot work, right?
Naive one is also work, yeah.
But why? I mean, so, okay, if you assume that your theta with parameters, right, are sampled from, let's say, factorized Gaussian distributions. Let's say your D prime is a factorized Gaussian distribution. Okay, which means that your weights are not correlated.
Yeah.
Right? Then it means that theta and theta tilted should be independent Gaussian variables, right?
Yeah.
Then in expectation, I would say theta is after this change has the same kind of distribution, right, as let's say your original theta.
Sorry, which one?
The naive one.
Naive one. Yeah. So the point is the theta is first randomly initialized and fixed. So.
But then theta tilted is also independent samples, right, from the same Gaussian distribution. I think the question here is, my understanding of this naive one is after this procedure, your theta, mu theta, right, is still like independent samples from factorized Gaussians.
Yeah.
Maybe I can add something that helps. M is learned.
Yeah.
So because of that, it's not. So you first sample theta, you learn an M, which is the mask. You use that to prune, and then you reinitialize the weight. So because M is learned, it doesn't work the way you think because there's a learning process in the middle, which is not like random.
It's so weird.
It is weird, and my question was actually,
Yeah.
have you looked at what is the distribution after you do this process?
After?
What will happen, so like after you apply the naive randomization, maybe even multiple times if you want to, you're going to get now a new theta that has been created by this like pruning stages and reinitializations. And the question is, what distribution is the theta coming from? And it's not going to be from the distribution, the initial distribution. It's going to be something different.
Yeah.
Do we know how the distribution looks?
Actually, I don't have the answer.
I think that would be interesting, because that would mean that there is a better distribution to where it's from.
It's interesting.
That was my question. Yeah. What is the actual distribution after this process?
I also had a question, but maybe the easy to figure out if the question makes sense. Is this specific to classification? Like, does this only work in classification settings? No?
This also works. I actually forget, but I tried. I confirmed this method in some language task, but it is also classification task. It may be also.
So I don't know this literature, so maybe I'm a bit lost. But like while you're presenting it, I'm thinking of like all these papers on theory of random projections.
Mm-hmm.
So like especially classification, right? Like if you find nice random projections that just separate data and make it linearly separable,
Mm-hmm.
that's why classification works, right? So
Mm-hmm.
to me, this, I don't know, maybe I'm misinterpreting it, but it sounds like, especially like the Gaussian randomization, is like doing some things at random, like finding random projections, they're maybe like frequency preserving, but changing the angle so it gets better separable, and that's like why it works maybe? Is that like kind of correct, or am I off?
So I'm not sure this will answer your question, and if we recall the theory of strong voltage gate, the expressive capability of the strong voltage gate is almost same as the neural networks, right? So they show the fact, which is strong voltage gate can approximate any target neural network, which its values are bounded by a finite value. Yeah. Yeah.
It's just a very
There's a question here. Oh, sorry.
No, actually, it's, I think I share the sort of concern of Yingzhen. I don't see in the naive randomization procedure what changes between initialization and
I cannot see what you faithfully defined.
so no, I have to say I don't see, and the reason is that for me, from a just modeling point of view, or the distribution, the joint distribution of the network is the same at initialization and even after learning the rest.
How it works. Okay, I can tell you.
Okay. So let me. Sorry.
She seems to have the answer.
Yeah.
My previous conclusion actually comes from M, right? So the interesting thing here is that theta tilted, now the new theta is no longer like independent with the previous theta, because M there depends on the entire theta. So when you actually say mask copy other things and it's re-initialized, right? This mask state itself is also a random variable condition on the previous theta. So at the end of the day, the joint distribution will no longer be Gaussian.
Still weird.
Sorry. Let me proceed to the next slide. This may answer your questions, I believe. And we have a theoretical support for the iterative randomization, and this supports our hypothesis in the initial hypothesis. And the following theorem says that if the pruned weights are randomized for enough times, then the logarithmic overparameterization becomes unnecessary in principle. So this supports our hypothesis that iterative randomization virtually increases the number of parameters. And in this theorem, this R is the number of randomizing iterations, and this is overparameterization factor required for approximating the target neural network, and this involves the logarithmic factor, and also this number of iterative randomization as the denominator of the factor. So obviously, if we set this R to be very, very large, then we ignore the logarithmic factor. Then the factor converges to 1, so we can remove the logarithmic factor. This is how our randomization works for strong root etiquettes.
Cool. I think I can understand this, but I kind of just wanted to repeat like a tweet that Yana Kun had when some of this kind of stuff in this space kind of came out, which is learning M is the same as learning theta. And basically coming to your theorem, like, okay, I can understand the mechanics of it, but in the end, like every iterations you need to relearn M to figure out what you prune. Do you gain anything? Like computationally or otherwise? Is this the same as just training the big model, but you just like split it into these kind of iterations without necessarily gaining much?
Thank you. That point will be explained in this.
Okay, so your claim is that you actually gain something by doing this process.
Yeah. Actually, the computational overhead is almost free, and this experience shows the improved accuracy for free in terms of the computational efficiency. And this is one experiment on ImageNet with less than 50 layers, and the left figure shows the training accuracy and validation accuracy during the optimization of M. This x-axis is the epochs, which is the same as the standard training by SGD, and the green.
So this includes also the epochs to train M.
Sorry.
This includes also the time to train M.
Time.
To train M.
No. This is.
This training M.
Oh, this is just training M.
No,
you have to train M and theta at some point, right? You train M multiple times, and at the end you train the theta.
It's never trained.
It's
never trained.
never train, but randomly replace.
Oh, just randomly sample. Okay.
Yeah.
Okay.
Thank you. And so the left figure shows the improved accuracy for free, and the right figure shows the comparison to the standard weight optimization by SGD, which is the blue one, and this is the model size accuracy trade-off figure, and this is somewhat like unfair for SGD, but actually we have the improved accuracy in this trade-off curve. Okay, I'll skip the second experiments.
So maybe just final comment. I'm sorry, I know that you have to move on. I really want to see the last part of the talk. But no. Like,
sorry.
I hope you will have enough time, even though we are asking questions.
Yeah.
But I feel like it's kind of defeated the purpose. Like you said, there is logarithmic ticket hypothesis. That means there is a sparse network, and then you learned it, but then you added more weights anyway.
Yeah.
So you are contradicting the lottery ticket hypothesis, right?
Yeah, actually.
Yeah, fine.
Thanks. But the point is the pros of the strong root etiquette, the practical benefit of strong root etiquette, which I explain by this. So which is we can use any distribution like discrete distribution. So we can optimize some discrete neural network, and this pros is also for our algorithm. Okay, right. Thanks. Sorry.
We're not moving on.
Yes, sorry. Just very because here you actually show this partial organization, and then if you show this plot where the red bar is actually better, right? And here is actually you only kind of assign weights to only like 10% of the room, right? And then I guess you do this iteratively, right?
Yeah.
And then I'm just curious, like if you do partial organization, like for example 0.1, R equals 0.1, like in the end, what is kind of like the percentage of weight that's actually getting pruned? Like what is like the sparsity
rate?
Yeah.
It's good point, and I did not explain, but in this optimization of N, the sparsity rate is fixed as the same rate because we first randomly initialize N by some sparsity rate, and we don't change the sparsity rate, but we optimize which is 1 and which is 0 with the same total number of sparsity rate.
So that in that involves like in your next slide, so it's actually like you compare like the difference like R, the choice of R is actually like always on like in the end it's always the same sparsity rate.
Yeah. Actually, the M part is not changed, so the sparsity rate is not changed. Please believe me.
Thank you.
Thank you. Okay, so let me proceed to the next one. Sorry, I want to discuss with you after this talk. Okay. The second one is meta ticket I called, and this is the meta learning of the connectivity for quick adaptation, which combines the structural plasticity and the synaptic plasticity. And the formal research question, instead of the previous informal one, is stated that does the rotate ticket hypothesis still hold in the limited data regime? So few-shot data regime. This is our research question. More specifically, we investigate the following questions. The first question is, within a random initialized neural network, can we find a sparse network that can achieve good accuracy by quick adaptation with the limited data, given limited data? And the second one is, what is the benefit of the sparse structure for the quick adaptation? So to investigate these questions, we designed a simple meta-learning algorithm based on strong rotate ticket method. And the algorithm is very simple, and we want to optimize the binary mask n such that the subnetwork can adapt to various tasks with few short data, right? So this M is the sparse structure of the network, and if we given a few short training data from some task, we optimize the M so that it can quickly adapt to the training data without overfitting. And this large capital N or capital F is the mapping of in-optimization that returns a random parameter, which is actually a simple gradient descent of few iterations. And the point is that this initial parameter phi 0, this is actually the same one as this phi, is fixed with a randomly initialized value. So in the same sense of the previous work, well, strong rotate ticket. This is the point. So we can expect just that M has a sparse structure with good that can run efficiently and with good generalization. And this algorithm can be considered as a weight pruning counterpart of MAML, which is a very well-known method in meta-learning and few-shot learning. So by comparing our method and MAML, reveals the differences of weight pruning and weight optimization in the context of few-shot learning. Okay. And from here, I explain three empirical observations. The first one is MetaTicket is a rapid runner compared to the weight optimization counterpart MAMU. And in this experiment, we compare the inner gradient norms. Inner gradient is the gradient in the inner optimization of the feature extractor of the model. So this experiment confirms whether the feature extractor adapts quickly to a given few-shot data. And the blue one is the inner gradient of the MetaTicket, and the orange one is that one of MAMU. And this shows the inner gradient of MAMU goes to almost zero as the meta training converges, but the inner gradients of the MetaTicket do not vanish or rather increase. This is an initial inner gradient for each task. So we can see that MetaTicket is in MetaTicket feature extractor is rapidly run, but in MAMU the feature extractor is reused for every task. So it can be considered as something like a pre-trained feature extractor. So we can expect that MetaTicket has a superior meta-generalization, especially when the feature extractor needs to adapt to novel tasks. And this is in this experiment, we confirm the previous expectation of meta-generalization. And so this table shows, in this table, we evaluate the meta-runners of MetaTicket and MAMU on the tasks from unknown domains, which is does not seen in meta-training phase. So if we see like C-pattern to bridge G-flower or bridge G-flower to C-pattern, we can confirm that MetaTicket improves the cross-domain generalization due to the rapid learning nature by weight pruning. And the similar results can be confirmed with resonance family. Sorry, if you have a question, please don't hesitate. Sorry. And the last experimental result is on the power of sparsity structure. And here our question is, how effective is the sparse neural network structure itself for few-shot learning? And here, to remove the effects of initial parameter phi 0, we enforce the very extreme setting to the phi 0, such that all parameters in phi 0 are initialized with a single same constant. So we can see that the distribution is Dirac data distribution. And in this setting, MetaTicket cannot exploit any signals or scales in phi 0. So we can observe the effects of the sparse structure itself in few-shot learning. And we use the OmniGrowth dataset, which is a few-shot benchmark for classifying characters of various language. And this left table shows a comparison with random mask and the optimized mask. And this result is surprising for us because we don't have any signals and scales in phi 0, but the random mask and optimized mask completely different results. And also, this is a fun visualization for us. And this is a visualization of the first layer of the meta ticket of the MLP. And so this shows how each parameter are sensitive to the input dimension. And this shows some locality pattern which is meta-learned by this method. Okay, so that's it. And here I like to summarize these two papers. And in these papers, we combine the combination of these methods reminds us the brain mechanism of structural plasticity and synaptic plasticity. And the first paper corresponds to the structural plasticity of pruning and regrowth. And the second paper combines the two structural plasticity and the synaptic plasticity. Okay, so I think the future directions are as follows. And the first one is the applications of this strong rotate ticket approach to large-scale training with low weight distribution, like this discrete distribution, which would be practical if strong rotate ticket can be applied to language models. And also, I wonder during this workshop, can we reformulate the strong rotate ticket from a Bayesian viewpoint? Or this is the next one is the existence proof of meta ticket, which is non-trivial from the previous strong rotate ticket theorem. So these are future directions. My quick talks. Any questions?
I just had two quick remarks
Yeah.
for the second part. The first remark regarding the second part of your work. So I don't know if you know, but there is a paper, Task Diagnostic Continual Learning by Ohm, who is basically doing something quite similar, formulated in a Bayesian way, but doesn't connect to the lottery ticket hypothesis at all. So you might find that quite interesting. It's applied to continual learning, so it's not applied the same way, but it's exactly the same thing. You have a mask, you have the parameters, and you meta-learn the mask while you're learning the parameters, so it might be an interesting point for you. The second point I wanted to make on the first part, there's some folks at Mila that I'm happy to put you in contact with that were going in exactly the same direction, and one thing that they were doing is, besides just learning the mask and pruning and adding weights and pruning, they would also learn theta from time to time, and they said that made a big difference. So maybe something to consider, like not just sample and mask, but also like fine-tune theta from time to time. It actually gives big boost.
Interesting, and
we can chat by email.
Yeah. Thanks. Any questions at this topic? On this topic? Okay.
Yeah, I have a short question about the strong lottery hypothesis.
Yeah.
Because I remember there's some work from some years ago in the sense that like you would have to pre-train, I don't want to say pre-train, but you had to train your initial weights a little bit, and then you could find a good mask, a good lottery ticket.
Yeah.
Yeah. Would this kind of thought also apply in this case, or is it important to like keep the strong lottery ticket hypothesis?
So the point is initial parameters are pre-trained, right?
Like instead of restarting, if you're thinking about restarting to the first distribution, you can restart to the distribution after like 100 training stats or something.
Yeah. Actually, I don't have any answer, but it is very curious direction. But I didn't explore the direction. Sorry.
Thank you.
Thank you. Okay. So let's slide to the next topic, which is somewhat very immature research I started, which is the paper title is Transferring Learning Trajectories of Neural Networks. And the background is very different from the previous ones. And this is the era of foundation models. And now there are many foundation models available, which can be used for various tasks or domains by fine-tuning. It is so powerful, but any foundation model will be eventually outdated due to the old knowledge or incapability. So we usually fine-tune this foundation model of version 1 to the various tasks, but eventually we have to replace this foundation model to the version 2 model by something like retraining, with enhanced knowledge or improved generalization or mitigated bias or something like security issues. Then we have to retrain this new version 2 model to various tasks and domains. So our question is, how can we mitigate this retraining cost? In this scheme, there are several related approaches. The first one is obviously transfer learning or domain adaptation, which can be used to each fine-tuning or domain adaptation. Also, we can use model merging or task arithmetic to handle these fine-tuned models. And also, we can use to replace this foundation model, to update this foundation model to the version 2, something like continuous learning or knowledge distribution or just training from scratch, and etc. But we think none of them mitigate the retraining cost of each fine-tuning. So our approach is something called learning transfer, which transforms the learning trajectories for each domain or task to the version 2 model. And if we can successfully do it, then the fine-tuning of the version 2 model will be largely reduced low cost fine-tuning. This is our main idea of our approach. So let's dive into more mathematical perspective. And first question is, what is the learning transfer? We define as follows. When a learning trajectory of the version 1 model, in the previous scenario, this is a fine-tuning trajectory of the version 1 foundation model, theta 01. And also, as new initialization or foundation model are given. Then we want to estimate this new learning trajectory for theta to 0, which is if we have some desirable transform pi, we can define this new trajectory by this simple linear formula combination. And here I note that T can be any time step index, such as iterations or epochs, but any time step can be considered. And the next problem is, what type of the transform pi should be used? And we focus on a permutation symmetry of neural networks, which is a simple transformation. It permutes the neurons and the corresponding connections or weights. That is, so it preserves the input-output relationship. So the permutation symmetry preserves the functional property of the learning trajectories. So we decided to focus on this transformation. The next question is, can we transfer a given learning trajectory by just permutation? The answer is yes, at least in the initial phase between overparameterized two-layered neural networks with independent random initialization by K-means method. This is the point. More precisely, let f theta 1 and f theta 2 be two-layered real MLPs with the intermediate dimension of n. So this dimension is capital N. Then we can show that there exists some good permutation phi such that the cosine distance of the expected gradient, the permutated expected gradient and the target expected gradient converges to 0 when this intermediate dimension grows very large, with high probability with respect to the randomization of the initializations.
Sorry, a quick question.
Yeah.
Why did you put the I would put the expectation outside, so I would just take cosine between gradients and take an expectation of the cosine. Why did you take the expectation of the gradients and then the cosine between the means? Is there a reason or just?
So the question is, the expectation should be the outside of the cosine.
Just wondering why the choice, why inside and not outside?
I not consider that.
Okay.
But I assume these are the two gradients on some dataset for distribution. So the two gradients can be transferred by just permutation. This is our theoretical intuition of the learning transfer. And also we empirically confirmed this setting and plot the this is the cosine similarity instead of the distance. And the different color means the different dimension of the intermediate dimension. And we confirmed that somehow this result can be confirmed in experiments in some level. Actually, this is 0.7 and not 1, but if we increase the intermediate dimension, we believe that it should be converged to more nearly one similarity. And okay, and I explained the algorithm for the learning transfer. This is called gradient matching along trajectory. So how can we find such a good permutation pi? So yeah, I have little time, so I have to quickly. And pi is expected to satisfy the two trajectories nearly same. But since we don't have this red one, except for the initialization, so we approximate it by mean batch gradient, or some batch gradient. Okay. This is a first approximation, and then this expectation to pi can be rephrased as this optimization problem, and this is a nonlinear one, but this is mathematically sound one. All right. So every terms rigorously defined, and this theta 2 pi is defined as in the previous slides. Here we use this definition, and this is nonlinear, but with some assumptions we can reduce this nonlinear one to iterative linear optimization. So we can solve this efficiently with gradient computations on t millibatches, and this t is the length of the trajectory.
Sorry, maybe just quickly.
Yeah.
So theta one of the trajectories given, and then your goal is to find the other trajectory maybe partially given, and then you're trying to figure out the rest. Is that something? So I don't know how you get the theta 2.
Oh, yeah. So our purpose is this theta 2 zero is already given, but we don't have the rest of the
Then
trajectory.
you're slowly going over to figure out.
Yeah. Thanks. So this is the animation of the algorithm. First, we have the old trajectory for the version 1 model, version 1 initialization, and also version 2 initialization. And first, we compute millibatch gradients for these ones and optimize the permutation by the linear optimization. Sorry. And optimize the permutation by matching the millibatch gradients and iterate this procedure until the last time step of the source trajectory. Okay, this is the animation. Yeah, I have just 3 minutes. The first experiment is linear transfer without training, without additional training, and the comparison is first one is the Oracle method, Oracle transfer. This uses optimal permutation, which can be computed by using both source and target trajectories. By matching them, we can obtain the optimal permutation if we have the true trajectories of the target network. And also GMT and FGMT is our algorithms, and naive refers to the random permutation case. And the left figure is the case of the transfer between independent random initializations, and the right figures are the case of the independently pre-trained initializations in this case on ImageNet, and transfer the fine-tuning trajectory. And so I don't have the time to explain, but the point is that the more interesting is the right case. This is a transfer between different pre-trained models, and in this case, the naive transfer by the random permutation cannot achieve beyond the non-trivial accuracy, which is random accuracy. But our algorithm achieve nearly Oracle accuracy until the middle step. The x-axis is the time step or the trajectory, but after the middle, our algorithm also degrades the accuracy by the transfer. So this shows the difficulty of the transfer between different pre-trained initializations. And the next experiment is transfer and then additional tuning, and compare to the standard training from scratch. And we can confirm the accelerated convergence after the transfer. And particularly in this case, the pre-trained on ImageNet and transfer should be fine-tuned trajectory. Then we have a 3 times faster convergence in the additional training. Also, we take some computation for learning transfer itself, but it requires as I briefly explained, it only requires gradient computations on only t millibatches. So it is t iterations of the learning. So here t is like 50 or 15 or 40 or something like epochs. So this is a promising result for us of the practical benefit of the learning transfer. And sorry, I over the 1 minute, but this is the last experiment, and this is before the previous experiment is pre-trained initialization, but they are pre-trained on the same imagement. But in this experiment, the old pre-trained model is pre-trained on the 10% of imagement, which is a little knowledge, and the new one is pre-trained on full imagement and fine-tuning on each task. And we can confirm that even if the fine-tuning itself is obtained from the old models with limited accuracy or generalization, the transferred one achieves an improved accuracy coming from the new pre-trained model, which is more generalizable model, and the additional training is faster than fine-tuning without learning transfer. So this is the take-home message. In transfer learning, we consider a single pre-trained model with multiple tasks. But in our learning transfer, we consider multiple pre-trained models with a single task and transfer between the pre-trained models. This seems, for me, seems fruitful setting. And future directions are as follows. And the first one is transfer over Adam trajectory, which is crucial for language models. And the next one is, can we get more accuracy without additional training? But this probably needs a new perspective to learning transfer, probably beyond the permutation symmetry. And also the last one is designing a transferable optimization algorithm other than SGD or Adam, which is my current interest and working on this. Yeah. Sorry for my broken English. That's all. Thank you.
Do people have questions? Like, how many questions do we have? We have 1, 2, 3. Okay. Sorry. Maybe.
Maybe we can take like 3 questions. Okay, feel back first. Okay, well, because it's pouring, maybe people are not going very far for questions. Yeah, let's do questions for a few minutes.
Okay, be quick.
Thank you.
Be quick. So thanks for talking. It's very
Thank you.
interesting. I feel like your idea of doing other things than really training the thing is actually quite interesting. It's like we always just fixate on just train the weight. And anyway, I think here for your last talk, actually I think what can be very interesting is to determine in advance like how many steps you can transfer without like getting back to random things, right? And I think probably there it includes some kind of estimating like the error interval or something like that. And here is maybe where like Bayes information can be helpful. So yeah, I don't know how that works out exactly.
Yeah, I'm very curious about such direction.
It's just a remark. Yes.
Thanks.
Thank you for the talk. Very interesting second direction. So I just want to understand how it can actually work. So your new initialization, right, is different from the first initialization, maybe even after commutation, right? So it means that let's say you find the best commutation to project the first initialization point to be the closest to the second one, then there is still a gap, right? Then the gradient trajectory seems to be different. So you're trying to somehow only use this commutation, right, to transfer the trajectory, and the trajectory, in some sense, the shape will be preserved. Only, the difference is only about from this commutation. So I'm just wondering, in general, why this can work.
Yeah. I think the point is, sorry, I don't have the experience on the actual running trajectory visualization, but I think the point is we approximate not initialization but gradients, but we approximate gradients. So the transformed one can be similar to the this is not the answer to your question. Sorry.
Okay, maybe I can rephrase it in another way. So I'm guessing that you are trying to find, let's say, the nearest local optimum, right, from the second initialization that corresponds to a sort of like symmetry mode, right, for the first local optimum you find. I think this is what I guess. But my main question here is, since you don't have exact kind of correspondence right after this commutation, so I would guess the trajectory for the second one will look different from the trajectory for the first one. But it seems that this trajectory for your method just work out.
So I'm not sure. I
Okay,
can.
maybe take this.
Sorry. But thank you.
For the strong Mariet ticket part, like the earlier part, it requires the logarithmically wider network for it to work. But do you expect it to work also for the large language models?
Sorry, what?
So at the end, you suggested to try to use a method for LLMs or any in general large models, right? And for SLT, it requires logarithmically wider, network for this to work. Do you expect this to work? And given that you've tried it on like 5-layer MLPs, do you have some insights on like applying it to much larger models?
So something like language models. Actually, we in our initial experiments, the strong root etiquette does not work on language models. This is one reason is that strong root etiquette is proved for NLPs, but not the models with attention mechanism, which is totally different from the NLP model. So the existence of strong root etiquette itself is the open problem for transform models. So okay, thank you.
All right, I think it's time for a wrap. Let's give him a big hand.
So today I'm going to be presenting some work I did with my colleagues Neha Gupta, Ben Adlam, and Jamie Smith at Google about ensembling over classifiers from a bias-variance perspective. And I actually got into this. So I got into diversity for classifiers because when I was a grad student, I worked on metrics for diversity. And something you'll hear a lot when you're thinking about ensembles is, well, if your ensemble is diverse, then you're going to have more robustness. And it really bothers me when that sentence isn't actually made precise, right? What metric are you using to look at similarity? Which space are you evaluating things in? And as I was looking at this problem, I kind of stumbled into duality entirely by accident. I didn't expect to find it. So this talk is very much, here's how I discovered duality as well, how it kind of like appeared where I wasn't looking for it. And so hopefully I'll be able to make that come through. All right, so this is one of my favorite quotes, in part because it justifies my entire research agenda, which is that there's understanding diversity is the holy grail in the field of ensemble learning. And we can see why that's the case from an intuition perspective. Because again, people have this intuition that if you work with ensembles, the more diverse they are, the more robust they are, the less sensitive they are to one ensemble member making a huge mistake. And you can actually see that this is mathematically true for the mean squared error if you just look at the bias-variance decomposition. If you just write it out, you have that the loss, the expected loss, we're not doing ensembles quite yet, we're getting there in a second, is equal to the bias plus the variance. I'm assuming that there is no label noise at the moment. And so if you rewrite this and reorder this, then if your distribution, if your expectation is uniformly over n models, then you can actually see that it tells you that the loss for the ensemble of n models is equal to the average loss of the individual models minus the variance, right? And the variance only depends on the data points, not on the labels. And so you have this very clean decomposition of the ensemble, the average loss, and the variance, where the variance is going to play the role of the diversity. So if you manage to have ensembles, or ensemble members that all achieve exactly the same loss individually, where this term is equal, the more diverse they are, the lower the ensemble loss is going to be. This is super clean, it's very pretty, and people have known this for a really long time. Unfortunately, something that people don't necessarily pay attention to when they work with bias-variance decomposition is the fact that it is actually a decomposition for the mean squared error loss. It doesn't hold in general. And so the question is, can we try and achieve something similar with classification losses? And the main issue we're going to run into is that typically classification losses are not symmetric. And so this is going to cause a lot of problems, but then also create a lot of beauty. So before I get into the math of things, when I started working on this, for me, the bias-variance decomposition was very much, like a statistics or machine learning 101 statement. It was very much something that you see in your intro to theory classes and then never really touch again. But then again, as I'm sure you're all aware, it has made somewhat of a resurgence with the double descent phenomenon, and a lot of people have been looking at it to understand various deep learning behaviors, essentially. So here are a couple of papers, but I'm sure you can find 30 more in the past 3 neuropses or something. So because we're going to be staring at this a lot, I took the liberty of writing this down. And so really, so we can understand it in detail, because this is a talk about the bias-variance decomposition. So we're going to be really thinking about a given point and a given label. We're not going to be looking really at average losses over data sets. We just add initial expectation, but it's going to be a little annoying to carry that extra term around. So at point x, with a prediction f of x and a true label y, we can decompose the loss of our predictor f into 3 terms. The label noise, which as you can see is the first term, does not depend on the predictor at all. As soon as you have any kind of label noise, you have this irreducible term. No matter how good your model is, you're just kind of stuck with it. Then the second term is the bias. It's essentially the loss between the average label and the average prediction. And then finally, the variance, of course, which is essentially the deviation from the model to its mean. Right? So these 3 terms, we're all super familiar with it. This is from a paper in 1992. And the aside from being this really useful tool that we use to understand how we can reduce our loss and where the main sources of loss are coming from, the bias-variance decomposition is also really useful for slightly more complicated analysis. For example, the law of total variance will give us that for any 2 random variables, you can decompose the variance due to 1 random variable into 2 terms, the explained variance and the unexplained variance. And so this is something that's actually extremely useful if you have different sources of noise that are coming from in the same learning procedure. Let's say maybe you have randomness in how you shuffle the data, and you have randomness from initialization. This is one way to kind of disentangle how these 2 contributions come from. And so it's really important to have this variance term, because then we can leverage all of the analysis that people have done about variances in the past and fall on your feet. It's also really nice, as I mentioned, to think about ensembles. And not only because I specifically care about understanding how diversity is important in ensembles. More generally, it gives us a lot of really cool facts. For example, and this is not super surprising, the expectation is linear. And so when you take an average of models, then you can also see that the bias itself is going to remain unchanged. And then simply through Jensen's inequality, you can see that also ensembling will always reduce the variance. And so assuming no label noise, bias is constant, variance is reduced, ta-da, we know that our overall loss is going to be improved. Right, so this is really nice. And so it also gives us this really clean understanding, once again, for the mean squared error, of why we actually want to do ensembles. And we can also do a lot of cool things as understanding like how fast the ensemble is going to converge towards the mean prediction and so on and so forth. All of this analysis is really easy to do. And this is, I think, the last slide where I try and convince you this is an important question, and then we'll get into the math. We do care a lot about ensembles. Admittedly, I made this slide before everybody started doing LLMs like nonstop, where you can't necessarily always assume that you're going to train 10 ChatGPTs or whatever. But if you actually can afford to replicate an experiment several times, ensembling is the quickest, simplest, easiest, embarrassingly parallel way of improving your model, right? If you've actually trained the same model multiple times, maybe even tried different hyperparameters, you can just recycle them, right? You can ensemble them and like use that. It's gonna work great usually. There's a lot of literature on these kind of hyperparameter ensembles as well. And so it's all well and good for the loss, right? We've shown that it will be reduced. But experimentally, we've also seen that it also works very well for things like calibration and uncertainty. So this is from a paper from 2019 from my old group. There are so many other papers that will tell you exactly the same thing, where essentially you look at the accuracy of different methods on, let's say, ImageNet, and you can kind of see that even these Bayesian methods are kind of like losing to ensembles, which are, again, embarrassingly easy to do and maintain much higher accuracy as you increase the difficulty of the dataset shift. And the calibration right now measured with the expected calibration error also remains really low compared to all of the competitive methods, right? So again, this is not really new. This is 2019. A lot of people have replicated this experiment since then. But most of these experiments, most of these cases where we've seen and happily stated if we do ensembles, we're going to have a more calibrated model, are not typically looking at regression tasks. They're not typically looking at the mean squared error. And often they also say, okay, and we're going to try and use diverse ensembles, right? So that's my own pet peeve. But the fact is, in the end, we're not looking at the mean squared error for our evaluation tasks. We are looking at different errors. So the question is, how can we actually think about this a little bit more clearly? Great, now's the math section. Okay, so we've all heard at this point about Bregman divergences, but I'm still gonna walk you through them one last time. A Bregman divergence is essentially defined by a strictly convex differentiable function f. So it can be the entropy function, it can be the L2 distance, and so this is going to define your Bregman divergence. This way you get the mean squared error, you can get the KL divergence, you can get Ikura-Saito, and so on and so forth. And really, I think we actually saw this picture before, but again, one way to think about it is really just looking at the linear approximation of a convex function. If you have your 2 points, x and y, and your corresponding f of x, f of y, you take the tangent in point x and try to approximate what the actual value of f of y would be if you only had access to linear models. This is what you would end up with. And so the Bregman divergence is really just the distance between these 2 points. So it's not a distance, but it is guaranteed to be positive. It has a lot of nice properties that kind of are distance flavored. And it's not really a surprise that they end up showing up a lot in classification losses for all of these reasons, or in losses in general. As I mentioned, the mean squared error is a Bregman divergence. We also saw that technically any Mahalanobis distance is going to be a Bregman divergence, and those are, I believe, all the symmetric Bregman divergences. But then you can do a lot of cool things. If you take the entropy, you're going to end up with the KL divergence, or the generalized KL divergence, but as soon as you have probabilities, everything sums to 1, so it all works out. And I just want to draw your attention to the fact that we are going to be working with a strictly convex differentiable function, and you know it's going to be like a nice result, in my opinion, if you're actually going to have to use all the assumptions. This is going to be super useful. All right. So at this point, let's assume that you've taken maybe one class in undergrad on mathematics, and I've dumped you in front of you this problem saying, okay, well, we have the Bias-Variance decomposition. Please write the Bias-Variance decomposition for Bregman divergences, not just for the mean squared error, right? And you've only been to undergrad, and you probably didn't have a lot of coffee this morning, so you're not gonna think really hard. You're just gonna say, well, okay, I know where the mean squared error is. This is very obvious where the minus signs and the squares are. So we're just going to take that, and we're not going to think too hard. And we're just going to turn that into a Bregman divergence. This is probably going to be fine, and nothing is going to be wrong with this. That is not true, obviously. Otherwise, I really wouldn't be giving this talk. It actually turns out, and this is not obvious, that the Bregman divergence we're using also shows up in the expectations everywhere. The fact that we have the expectation of y here the fact that for the mean squared error, we had the expectation of f, that is actually a property of the Bregman divergence. In general, the correct way of writing this, if we want to be very precise and also correct, is to write them, I've written here by y hats and f hats. People typically call them central predictions and central labels. And they have these kind of not so nice definitions, right, down here at the bottom, where your central label is the argument of the expected Bregman divergence from y. And our central prediction is going to be the same thing, except we're taking the argument to our variable as opposed to from our label, right? And this is maybe the first time where it becomes apparent that once we move away from the mean squared error, and once we move away from symmetric functions, this is going to become painful. Because when our function is not symmetric, we can't just say these two things are the same. And that is extremely unfortunate, because one of the nicest things about Bregman divergences is this equality at the bottom. This is always true. It's super pretty. I really like it. And so if our function were symmetric, we could just take this term here, we could flip the z, we could flip the f, we'd end up with our same function here, use the same result, and say that this f hat is actually just the expectation of f. And everybody would be happy, and our sad attempt at generalizing the Bregman divergences would have been correct. Unfortunately, our function is not necessarily symmetric, and this is not going to be true in general. In general, we're not going to have this equality at all. We're just going to have to walk around with this somewhat unwieldy term, which hypothetically speaking, you were trying to write a paper about, would hypothetically make all of your proofs be 3 pages longer than you want them to be. And so here, yes?
Do you mind giving just a short intuition why the left-hand side is true and the right-hand side is not true? It's okay. Possible.
It comes through very cleanly on the left-hand side. If I'm going to be honest, if I try to rederive it right now, I'm going to embarrass myself. But we can maybe do this afterwards. And then the intuition for why it's not true on the right-hand side is really just the break of symmetry, right? Because we're not actually working with a distance. We've artificially created a duality between the labels and the predictions. And so we can't actually just treat them the same. And so the average, the quote unquote distance, right? This is essentially what we're doing is distances, right? These terms are as close as we can get to a distance with something that's not a distance. Because of the lack of symmetry, they're not going to be the same. But excellent question. Okay, so at this point, I want to be a little philosophical and make a statement, which is that if you have a mathematical result and the mathematical result is not super pretty, maybe you either haven't figured out the correct result yet, or it's pretty but you don't know why. It's a philosophy. I'm not saying it's true, but this is how I think about things. And I'll admit that when we got to this point, we were like, okay, well, hopefully this is pretty, but we don't understand why. So now we're really going to start hitting duality. Remember that we have our strictly convex differentiable function. It has a convex conjugate. You know all of this. I also wrote it the other day up here. Really, you have your primal and dual spaces. They're defined by your function f. You can bounce back and forth between the primal and the dual by taking the gradient of f. And because it has a convex conjugate, you move from the dual to the primal by the gradient of the conjugate of f, right? And you have involution, the dual is the primal. You have this nice way of just really bouncing back and forth, and this is where the strict convexity is important. You have uniqueness of this function. So technically, you can also show that the gradient of f is invertible with the inverse equal to the gradient of the convex conjugate. So let's go back to this, which was ugly and made us sad. There's one last equality. I swear this is the last time I make you look at inequality. Okay, this is the last time I make you think about inequality, which I actually wrote up here. And this is the other second super pretty result about Bregman divergences, which is that even when they're not symmetric, you can actually switch the order of the two arguments if you move to the dual space, right? So the divergence of x to y is equal to the divergence of the convex conjugate from the dual of y to the dual of x. If you really don't want to think about this too hard, if you add stars everywhere, you can flip the argument, and then you're going to be fine. So we're going to do that. We're going to add stars everywhere, we're going to flip the arguments. And now we're super happy, because now we're back to the point where our minimizer is in the second position. So now I can use the same result as before. It's the expectation, right? So now we have that our central prediction, which was painful and unwieldy, is just going to be the expectation of the dual of f. And then because you need to move back into the primal, because technically we're minimizing over z, but our argument is z star, we have to take another projection. So really, what we're saying is that to take the expected, or the central prediction, you have to first move to the dual space, do everything like you should, right? Everything's linear, everything's an expectation, everybody's happy. And then because technically you were in the primal space to start with, you do have to move back. And so you have to take a second step back into the primal. And so this is why I think this result is really pretty. It really tells us that when we added asymmetry, right? Oh, I forgot to say this. All of these results up until here were known. These are from a 2-page paper on arXiv by David Pfau. All we really did is say like, hey, actually, this is pretty. But again, we didn't actually do a lot of work until we got to this point. But really, the point I want to make is because you used an asymmetric loss, then you have defined two separate spaces between the primal and the dual, where the primal is the natural space for labels, and the dual is a natural space for your predictions. And if your function is symmetric, if you're working with the mean squared error loss or any other symmetric Bregman divergence, these two spaces are actually superimposed. And so you actually have, this is still true. Wait, actually, let me move. Okay. So this is our actual generalized bias-variance decomposition, where I'm defining a fancy expectation as the primal projection of the dual expectation, right? And you can see that everywhere we have exactly the same bias-variance decomposition, except anytime we operate over the predictions, we have to do it in the dual space. And everything is identical. We still have the irreducible noise, that hasn't changed because that was still always in primal space, it's going to look identical. And then the loss between the average model and the average label requires that the average model be computed in dual space. And it's the same thing for the variance. But again, if our loss is symmetric, everything remains the same. The primal and dual spaces are actually superimposed, and we have the same result as before. So technically, if you really want to be extremely precise, this has always been the bias-variance decomposition. There's always been a primal and dual space. They just were identical, and so nobody noticed. But this has always been happening, and it becomes extremely apparent as soon as you add this asymmetry.
So
Yes?
is the let EX be that kind of let EX be EX star star, but this
Yes.
is that X and the point X is not the same, right? Like they mean Y or should that because E is
Oh, sorry, it should be an F. Sorry, technically there should be an F of X.
F
but-
X, so
yeah,
Y,
yeah.
the Y space.
Yes, yeah, sorry. Or more generally, if I just take an arbitrary point, this is going to be, and it has a dual, this is going to be our definition of a generalized mean, essentially, or a dual mean.
And it's always happening in the label space.
In the prediction space.
Sorry, the prediction in the label space are
Not the same.
do so we should have just
Yes, correct.
Maybe I have a
Sure.
question. I'm very nice on this, but if you want to take mean in white space versus, let's say, this interesting dual and projective mean, right? So how would they differ depending on, let's say, this f function?
What a fantastic question. No, this is a great question. I'm going to answer it in detail in a few minutes. Do you mind if I get, letting me get to it?
Yeah.
But yeah, no, that's the question, right? I 100% agree. Okay, not to beat a dead horse, but maybe just one last time. The correct space to think about predictions is a dual space. You move to the dual space by taking the gradient of your convex conjugate convex function, and your convex function is what defines your loss. So your dual space depends on the loss. It's not very surprising, but if you just really train machine learning models and don't think about this too hard, it's worth insisting upon. Some concrete examples, as I've mentioned several times, if you take the mean squared error, you have the dual mean is actually equal to the mean. That's going to be true as soon as your divergence is actually symmetric. I hope that came clear over the talk. If we take the KL divergence as our Riemann divergence defined by the entropy convex function, then we have the dual mean as essentially the expectation in log probability space, right? So the dual is going to be log probability space. You move back to the primal with the softmax. So at least this is a question I've asked myself in the past, which is, I'm ensembling classifiers. Do I ensemble the logits? Do I ensemble the probabilities? You didn't know this, but this was what you were wondering. You were wondering if you should use the primal or if you should use the dual. And so here's maybe the first part is going to start addressing your question, which is, let's say that, and I think this is the plot. It's actually going to be here several times, so it's always going to be the same plot. Let's say that we've trained an ensemble of neural networks, ResNets, I guess, at the time, with a cross-entropy loss. And we've ensembled them naively, so we're ensembling probabilities, right? Because the probability space is the primal space. Then you can see that we have here the error, the bias, and the variance. The bias plus the variance is equal to the error because, again, no label noise in this experiment. And you can actually see, and this is, well, this isn't nice, is it? The bias, which should be constant, if we were actually looking at the correct, quote-unquote, correct bias-variance decomposition, is not constant. It actually reduces over time, right? I mean, not by bunches, but I mean, this is not a constant function, right? A couple of other things that maybe I'll skip over because I don't think this is the most experimentally oriented audience I've ever had, but a couple of cool facts, blah, blah, blah. And then there's like this interesting question of how do you actually estimate these quantities. It becomes like really slightly annoying to actually do correctly because you have a lot of fun bootstrapping experiments and so on and so forth, and like irreducible errors. But I will not be talking about that today. Oh, and one last thing. I think I'll say this later, but just to mention it now. Right now, the bias is being reduced. That's not actually guaranteed to be the case. You can actually see the variance, the bias increase. This does not actually happen on this data set because it's averaged over a bunch of points, but there are points over which you actually have a bias increase, which is even more troubling, in my opinion, than the fact that it goes down. Like going down, it's an ensemble, okay, I guess. No, going up, that shouldn't be happening.
So what do you say, bias, you mean bias squared?
It's the bias squared, what do you mean?
Yeah, bias is sign.
Yes, yeah, the bias is sign, yes.
Yeah, because you say bias and right bias.
Of course, yeah, no, you're right. Okay, so.
The error comes from in bias.
It comes from both, but it comes mostly from the bias, yes. Okay, so now that we have a lot of math, and that I've been happy about duality for 25 minutes at you, what can we actually do about this, right? First of all, we had this nice bias-variance decomposition, and I was saying variance, and everybody was happy because it was the actual definition of the variance, right? Now I've introduced this weird Bregman divergent variance, and so there are a couple of questions about whether or not I can actually just keep using the term variance or not. And then, as I said, we've seen some like kind of weird behavior happen when we ensemble in the primal space. What if we ensemble in the dual space, I hear you ask? Excellent question. So let's go through a couple of these. First of all, in terms of what kind of variance we're dealing with, well, there's a couple of things that we're going to want to have, right? If I'm going to tell you something's a variance, you're going to probably want it to be at least greater or equal to 0. That seems normal. You're going to want it to tell you something about the behavior of the random variables you're working with. And earlier I was talking about the law of total variance. And as I said, this is actually something that some people care a lot about because it allows you to disentangle various sources of noise. It would be really nice if we could have something that looks like this again. Yeah, I just said that. Okay, so the first case I actually wrote the variance up here so you can still see it. It's an expected divergence, so it's going to be positive. We're good, that's fine, that's easy to see. The fact that the variance is 0 so predictions are almost certainly constant is also fairly straightforward to prove. The last term is almost true, but not quite. It's even better. It's even better because what you would want to have, which is expectation of variance plus variance of expectation, is actually going to say like, wait, no, you can't just take expectations willy-nilly. You have to take them in the proper space. And so this is going to be true if you take your expectation in the dual space. And this is actually the point in the paper where we realized that we probably had something really interesting because we actually see that this dual mean, right, this mean in the dual space is actually showing up everywhere, with equalities that we know to be very important, this is just a straight up generalization of them. Okay, so this was for let me see if there are any questions. Okay. Yes.
Maybe just about the equations, so like the two variants, like the two, there are two variants in like both terms.
Yeah.
So the variance actually is kind of like work on different space, and also not the same definition.
Yeah, so actually the variance that we have in here too is going to be this definition here. So it actually also has the dual space in it. Yeah, sorry. I should have made it a curly V, but then it just really gets unreadable, and I didn't want to inflict that on everyone. But technically, there's the dual space is also living here from this definition of the variance we're using for this proof, or for this result, where you're trusting me on the fact that the proof is correct. All right, ensembles. This is what got us here in the beginning. So a vanilla ensemble, a primal ensemble, as I'm going to be calling it for the rest of the talk, is simply an empirical estimate of the mean. And so when we have the mean squared error, as we know, it leaves the bias unchanged. It reduces the variance. We already talked through all of this. And so because the total is the sum of the two, it reduces the overall error. In the general case, as we've seen, we don't have the bias unchanged. We can actually show that the variance is still reduced as long as your divergence is strictly jointly convex, which is going to be the true in practice for most of the losses we're going to care about. But you can kind of you can artificially create some Bregman divergences where that property is not true. So you do have to be like a little bit careful, but in practice you're going to be fine. And so you're also going to have the same result where you need everything to be jointly convex in order to see a reduction of the error. And of course, this is true for the KL divergence, which is why even without doing all of this bias-variance decomposition, you wouldn't know what the bias and the variance are doing, but you could at least say that the error is reduced, again, because of Jensen's inequality. And yeah, this is sad. This is very troubling. I wish it weren't true. Or I guess it makes sense, but this is distressing, that it can increase the bias. Okay, so you asked an excellent question earlier, which is what happens if your ensemble in dual space? Let me tell you. Obviously, as you can probably guess, everything is going to be really nice and we're all going to be very happy. So, first of all, let's define our dual ensemble. It's not going to be anything particularly surprising. We're just going to do the same ensembling operation with stars everywhere. We project everything into the dual space, we take the expectation there, we project back into the primal space. Informally, because it's kind of annoying to actually define everything extremely properly, but you're all going to get what I mean. If you do dual ensembling, then the bias is preserved. It will be constant as a function of the ensemble size, and it will reduce the variance without having to make any kind of assumptions over the behavior of your Bregman divergence. So your Bregman divergence does not have to be jointly convex. Slightly more importantly to me personally, you also have what started this whole business, which is that you can actually write the ensemble loss as the average loss of your classifiers. So actually this is exactly the same, 1/n sum of the cross entropy loss of your individual classifiers, minus your ensemble variance, which, and this is very important, and I can go on a very long tangent on this, but I'll try and not do that. Your variance does not depend on the labels. A lot of people there have been a lot of attempts at generalizing this, quality diversity decomposition of the loss for classifiers. And a lot of the ways that has been done will actually still have a quote unquote diversity or variance term, which relies on the labels. And that, I would argue, is not great, right? First of all, because we know that's not the case for the mean squared error, but also more generally, right? If you're going to, the diversity of something should not depend on the label space, right? You're actually just looking at your function itself. Whether or not it's correct has nothing to do with whether or not your ensemble of functions is diverse, right? And so the fact that you can actually have an ensemble variance, again, it's up here, that doesn't depend on the labels, is actually really nice. And one last thing it means, the last thing you can do with this, if you are excited about this, is you can actually just you can evaluate the diversity of a function, you can evaluate the variance at any point. You don't need to actually know the labels. So if you need to do some kind of test time ensembling or whatnot, you can actually kind of use this as a metric to guide you as to which members you want to use in your ensemble versus not, because you can just use the diversity on its own. So that's kind of nice. Okay, actually I lied, so there are 2 plots, but technically the first plot was a subset of this one. So now I'm going to compare primal and dual ensembles. The primal ensembles are in full lines, the dual ensembles are in dotted lines, and the 2 graphs are the same, cipher 10, cipher 100, don't worry about it. Let's just look at one of them, so at the left one. So you can see that first of all, the bias for the primal ensembles goes down, we already knew this. It does actually remain constant in dual space. We knew this, we proved this mathematically. It's always still kind of nice to make sure that it works in practice for real deep neural networks who tend to be misbehaved if you don't pay attention to them too closely. And then we see roughly the same reduction in variance, and so because one of them reduces the bias and the other one does not, it does mean that despite the fact that our dual ensembles are much prettier and more mathematically correct, our primal ensembles, our vanilla ensembles, are actually going to achieve the lower loss. I think I actually just said all of this. Right. On average, this is an average. Here I took the average over all points in the cipher data sets. What's actually going on? Actually, I'll get to what's going on in a second. So, intuitively, right, or maybe for the rest of the talk, I guess, let's assume that our Riemann divergence is the KL divergence, right? We're actually looking at the cross-entropy loss in practice. This means that we're ensembling by taking a softmax of a sum of logs, right? I don't know if you've noticed this, but logs can go to -infinity when your predictions are bad. Unfortunate behavior of log probabilities. That means essentially that you have a phenomenon where if you have even one classifier that's extremely wrong, it's going to take over all of your other classifiers, right? Actually, you can also show this mathematically. It's a nice quality. I'll get to it in a second. But fundamentally, because you're taking this log, because you're doing probabilities in the dual space, in log probability space, you can have this behavior where just one really convinced ensemble is going to absolutely nuke all of your predictions. That's not the case for primal predictions, right? If you have like one ensemble member that says 0 and everybody else says like epsilon, you're not going to be saying 0. So that's essentially what's happening. You can write this out with this like really, really nice, in my opinion, arithmetic geometric inequality. I think it's always nice when these kind of show up naturally. But if we actually just look at ensembles of 2 ensemble members of 2 classifiers, technically you can show that you have better performance from the primal model as soon as you have a very big gap between the agreements of the 2 models, right? As soon as they're very unhappy with each other, which means one of them is going to be very incorrect, you're going to have one of them just kind of drag the other ones around.
Is there some kind of disagreement of this result with kind of proper scoring rules? That you really would like to have this kind of low probability behavior, and that's kind of what you would like to have, a proper scoring rule. That seems to kind of, you seem to kind of suggest that you don't want that.
You want, so,
yeah.
Yes and no.
So
this is a great question.
Because it's essentially saying that this is a life rule, never say never.
Yeah, exactly.
It's like if you say no,
yeah,
and you mean no, and it turns out to be yes, then you're infinitely wrong and you lose the life of gaming.
Exactly. So I'm going to, yes, that's a really good point. I'm going to say something, I'm not sure it's entirely accurate, but I think it might be related, which is one of the reasons why nobody can really agree on the right way to measure calibration in neural networks or in general, is because it's very difficult to entangle the quality of the prediction from the quality of the uncertainty. And this actually shows up when you're using proper scoring rules, which really you have to take both at the same time, which is really annoying.
Your response is not necessarily targeted for neural network at this point.
Oh yeah, no, this is general. It's motivated by neural networks.
That's why this.
Yeah.
You're saying something that kind of breaks my previous understanding.
Was your previous understanding that proper scoring rules were?
Is a good thing to do.
Yeah, basically we have a proper scoring rule because we're using Bayesian divergence. This is, I mean, it's not, we shouldn't be using proper scoring rules. That's really the, like, of all of the measures of calibration, please use that instead of the expected calibration error. Don't quote me on this. But also, this, as soon as you use, when you have a proper scoring rule, this is just going to be the case. It's not a criticism of them as much as it is something that happens when you use them, I think. Okay, so this is basically what I was saying earlier. The converse, though, is also going to be true, which is that if all of your models are like roughly good, dual ensembles are going to outperform primal ensembles because they're all dragging each other towards, like, it's a question of like how much influence the worst person has, essentially. For dual ensembles, the worst person can have like really, really strong influence if they're really bad. If they're already kind of okay, that's actually going to be a positive influence on the overall prediction. I also just really like this inequality, but okay, I'm going to probably end quite a bit early, so please ask so many questions. But there are still a couple of things I want to mention. First of all, at this point, if you don't remember it, you really haven't been paying attention. The Bayes-Variance decomposition has always lived in two spaces, and the only reason which is not necessarily obvious is if you have a symmetric loss, in which case they're superimposed. Operations on labels, or I should actually say operations on the first argument of your loss, which for classification is always going to be labels, live in primal space, which is why you're always going to have really clean expectations and a very nice definition of the Bayes error, even for classification. If you're operating on predictions, so on the second argument of your loss, then everything you do is actually happening in dual space. And so if you want to be able to prove mathematical facts or understand the behavior of what's happening, you need to actually do all of your operations in dual space, because this is actually the natural space in which they live. Because we are using a loss between these two terms, they have the same dimensionality, right? Technically, they're going to be an Rn, for example. But these are not the same Rns. They're, like, we can use them as inputs to a Python function, and it's not going to complain. But that should not be our baseline for being the same space. And we see here that it really isn't. Okay, I don't know what happened to my stars here, but essentially we have a really clean way of moving from primal to dual, dual to primal, which is defined by the Bregman divergence that we're using. So for, I don't know if I wrote it down. So if you're looking at symmetric losses, primal and dual, technically there's a 1/2 or like there's a 1/n that's showing up somewhere, but when you move back to the primal, you multiply by n, so it ends up being the same thing. And then I didn't write this down, but if you're looking at the KL divergence, which is what people are typically using for classification, what you have is a dual that is in log probability space, and then a primal, which is the projection of that, which is, you can show this, that's just the softmax. The convex conjugate of the entropy is the softmax. Yes, that's correct. If you use this decomposition, if you write the bias and variance decomposition using the primal and the dual space, you actually have exactly what we already knew for the mean squared error. So on the one hand, maybe it's not very novel. On the other hand, it's really pretty. And it does actually have a lot of implications because you do have to think about the dual space. And in particular, this is really, like, it doesn't really show up very often, but when you need it, it is incredibly important. Having the law of total variance, if we didn't have that, I think we probably would have just stopped writing the paper. That's how important it is to be able to actually maintain. And the fact that we actually have it, and the fact that it naturally shows up with a dual expectation, to me is possibly the most compelling argument for the fact that this is the correct way of thinking about the Bayes-Variance decomposition. If you decide that you actually don't like duality, and you're here, so probably you're not going to say that, but if you did, and you decided to do all of your operations in primal space, then, I mean, good luck. I mean, things are probably still going to be okay, again, because most functions we look at are going to be jointly convex. But it's the behavior of the bias, the behavior of the bias in particular is just going to be complete nonsense. And if you are just an experimentalist, you might not notice, but it's not enough. But you'll still, again, land on your feet thanks to Jensen's inequality. If we ensemble in dual space, if we do any kind of operation in dual space, I chose ensembles today, but you could do weighted ensembles or like weird things, you're going to have exactly the same analysis, exactly the same behavior results. that you would have if you were just looking at the mean squared error and regression, including, and maybe this is the last thing I want to say, an exact, an interpretable, and a correct, by which I mean not approximate, definition of diversity for ensembles. Even if you decide that you're okay with having labels appear in your definition of diversity, typically the way you'll have it is an approximation, usually like first or second order Taylor approximations of your loss function. And so you are lugging around this rounding error, which may or may not become incredibly painful to deal with. This definition of diversity is the KL divergence between the softmax of the law of probabilities and your classifier. Not only can I compute it, it's not even complicated, right? It's trivial to compute. So that's kind of nice. Which takes me to the end of my talk, unless you have some very specific questions, in which case you get to see the bonus contents.
Thank you. This was very enlightening. There's no total expectation. There was something in small print. It wasn't always valid. Huh? No, I remember. It was fine. As long as you do the expectation in the rule space.
Yes. And actually, you raise a good point, which I didn't bring up, but we have the law of total variance because we have the law of total expectation. So the law of total,
But you talk always about this classification, but this is also valid more general.
Yes, it is. This was started by my own quest to force people to think about what they're saying when they say, oh, our ensembles are diverse, which is why our ensembles of classifiers are diverse. But yes, this is for any Bregman divergence. It doesn't have to be classifiers.
Cool. Thanks for the talk. I have a lot of questions, but we have a lot of time, so I'll just shoot away. So the first thing, obviously, from a kind of Bayesian perspective, sometimes I might be tempted to think of an ensemble as a Bayesian model average, right? Where every member is a sample from my posterior. In which case, I guess the primal ensemble is the more naive, natural way to look at this. Do you think there's some semi-Bayesian interpretation for the dual ensemble?
I really do. I haven't had the opportunity to really dive into it due to going to do biological foundation models. But no, I really think there is, and I think it's going to be the same approach, right? Which is what's the space in which you do averaging? What's the space in which you apply Bayes' rule and your Bayesian interpretation? I haven't had the time to pursue it, but 100%.
The second question would be, so it seems like you have this trade-off, right, where the primal ensemble works better in practice, but the dual ensemble is a nicer thing to do. And for symmetric loss, as you said, that they're the same, so you kind of get the best of both worlds. So does that, in some sense, imply that maybe symmetric losses are the nicer thing to use? So if we do classification instead of using cross entropy, should we use the Breyer score or something?
So, good question. If you use the Breyer score, the models don't train as well, fundamentally. So you should, very empirically, you probably shouldn't be doing that. And I mean, again, right, we're thinking about the right way to measure things. We know that the Breyer score for probabilities doesn't make a lot of sense, right? I'm taking a little bit of a meta perspective on your question, but at least from that perspective, I would say no. I know there has been some research, and maybe MT knows more about this. I know he's played a lot with KL divergence of been symmetrized, or reversing the order of KL divergences. So one thing you could actually do perhaps is instead of taking the KL divergence, take the symmetrized, so half of x to y and y to x. You'd have to make, obviously, some assumptions about the fact that the labels are noisy or as an epsilon, so that you don't have, if you're working with hard labels, that's not going to work. But you could look at something like that, for example. I think that might work a little bit better.
Maybe it's a third question, which is not directly applied to your talk, but just on ensembles in general. I feel like there was this paper, and I forgot who the authors were, that claimed that if you take the amount of compute that you put into an ensemble, or the amount of parameters, and you just put the same amount into one big neural network, that might even actually work better, and that maybe it's not the ensembling itself, but it's just the additional compute and parameters. Do you have an opinion on that?
I mean, I do. I have a lot of opinions on that. Let me sort them. First of all, yes, empirically that's kind of true, right? I'm not going to we know that scaling works. Right, fundamentally, if I had the opportunity to either train the VIT G or to train like 10 bit S or bit B, then I would absolutely do the first option, right? For the same amount of compute, that would work better. However, first of all, just very strictly mathematically, if we can, and again, this is my audience, because often I say this to people and they're like, okay, but we don't really care. But mathematically, we know why this works for ensembles. The question is a little bit more complicated if you just do scaling. And then, when I say you can do any kind of like weird ensembles, that includes weird things you could do, including with, like your large LLM that you have at home or whatever, right? Because maybe you're ensembling not over different initializations, which is typically what people do for ensembles. Maybe you're ensembling over the current checkpoint, right? You have checkpoints over times 1 through n. Maybe you're going to reweight them. Maybe you're even going to do something kind of smart, which is, decay how much you care about them based on how farther away they are. You've not consumed any additional compute, right? Like you're still doing exactly the same thing. Because as you train ensembles, we're in a world where we have checkpoints all the time, and we're going to do some amount, we always do some amount of hyperparameter tuning, I think. I don't know, maybe someone who does not just trains the largest model will disagree with me. But we always have some amount of double checking everything looks nice and restarting. We're always going to have something we can ensemble. Whether or not we should is a different question. But yes, would I train 10-bit H's? No. But I might be able to do something smarter.
Yeah, thanks for the talk. Somehow any Bradman divergence can be written as the KL divergence between two exponential families, and then your dual space are the natural parameters, the prime space are the moments.
Yeah.
Does this probabilistic viewpoint add anything to the story? Or?
So, yes, actually, it's kind of interesting. One thing I mentioned very briefly in passing was that ensembles give you this nice analysis of how fast you can converge to the mean and how much of a variance reduction you have. Taking this perspective actually allows you to do exactly the same kind of analysis in the dual space as well. So actually it would have been true regardless, but when you write it with exponential families, it just is super pretty. I didn't include it though.
Thanks.
Just maybe a dumb question for the engineering problem. And if you're just doing the standard, multi-class classification with max and this cross-entropy loss, what does it mean to do ensemble in the dual space?
So ensembling in the dual space means you have n models, you take the logits of the models, average those, and then take a softmax.
Okay, so
And just to give the converse, ensembling in the primal space means taking the softmax so that the output of each model is a probability, and just averaging the probabilities. The question is do you average probability space or log probability space?
I see, thanks.
Yes, I have a very, very stupid question. So the definition of bias and variance here is very generic for Y and F. Why do we care about examples?
Sorry?
This seems to work for any Y and any predictor of F(x).
Yes.
Why do we care about examples? It still work, right?
Yeah, so this will always be true. We care about it. Actually, this is a really good question because this is what brings everything together. So let me make it, and I wrote it for the mean squared error, right? If you actually write the Bias-Variance decomposition for a single model, and then say your distribution is over n models distributed IID, it doesn't have to be IID, but it's easier to think about, then actually that also just gives you the decomposition of the ensemble loss as the bias minus the variance. And so that's why we care about the Bias-Variance decomposition for ensembles. It's because not because we care about the bias and the variance of ensembles, but because it allows us to understand what the ensemble is actually doing.
Okay, so thank you for a very nice talk and very nice problem and interpretation, of course, that we look at. In statistics, people have been working on generalization of expectation that they call quasi-arithmetic expectation, like geometric expectation. And what happens is that if you have, let's say, one expectation, you have a dual expectation. So basically, your E and calligraphic E are quasi-arithmetic expectations that are used in statistics in some papers.
Okay.
So this is a different problem, just from the viewpoint of statistics to average random variables, right? And there's one nice thing in this area is that we have a generalization of the central limit theorem. So instead of taking, if you have the empirical variance, you will have the CLT
Yes.
for your calligraphic E.
Yes.
I didn't have a look at your paper, but you do that.
So we ended up not including it into the paper because we were not submitting it to the right place. But we did actually like see that, and that's I think a little bit what I was telling you also earlier, which is so you actually have like I wasn't aware of this like geometric expectation, so this is really cool, and I'm really excited to read about it and learn about it. But we did actually kind of stumble into this as well, trying to understand if we could have a CLT in the dual space.
And there are some conjectures actually still pending, so I can point out some papers. So.
Yes, please.
Yeah.
But more generally, your point of like this has been done in like different fields gave us cold sweats for the entire time we were writing this paper. No, we ended up at like we briefly fell into like different like metrics and like an entire different world of publications, right? It doesn't intersect with machine learning at all, but kind of run into the same things, and that was really cool, but also a little bit stressful.
So why should you not have a CLT in dual space if there isn't a?
You do.
Yes.
I don't think we disagree. I think we
Okay,
do have.
I just thought there was a question that is there. Yeah, why shouldn't there?
I think we're all agreeing with each other.
Okay, sorry that I missed it.
Hi, just a very general question. So something that has been bugging me a little bit is the use of the double dual.
Mm-hmm.
So this is like, it seems to me from seeing your slides that should I think about the second argument of the divergence as always being the dual space? Or is it like a bit of an artifact that we use both to be in the primal space? Maybe should be first primal, second dual? Or?
I mean, because the primal is the dual of the dual, I think that's what you're asking, right? Are you just like asking in terms of semantics or? Wait, he doesn't. Frank.
He had it in his slides.
Yeah, it's very good.
Yeah.
So if you take it geometrically, there's no, it's a different thing. Something happened in center space. You explain it geometrically. But people have been like much global. To work on function Young loss. So he has probably good interpretation in different settings by using mixed parameterization, and then there's a kind of symmetry. If you look at function Young loss instead of Bradman divergence loss.
It's useful for continual learning as well.
Yeah.
I might just throw it. It's in the Hill Drive paper.
Any other question?
Thanks for the talk. So I have one question. If I do this averaging dual space, can it be a problem if different models have, so for example, different shifts in their logins? Because they
I see what you're asking.
Shift doesn't matter, right? So.
No, because they're all going to be, I'm trying to, so if they all have the same like shift, no.
Yeah.
Obviously because for exactly the same reason as usual. I think it doesn't matter in general because technically you're like the softmax is averaging not over like ensembles, it's like, it's a different axis, right? Which is like the sum on like the class labels, so I think it does work out. I think it's the same thing. I would have to double check, but I'm fairly certain it actually is okay. We can just stare at it together if you want. Yeah, because
I was just going to mention, I think that it seems like this dual, like ensembling in the dual space, it feels like something that's been done in terms of like margin classifiers in certain instances or database. You're actually like aggregating in that logic space.
Yeah.
Rather than the predictors itself. So I'm wondering, is there like, could you clarify any connections to margin losses and I guess interpreting?
Yeah, absolutely. So there actually have been some people have like written connections to this in the field of margin losses. In particular, there's this, it's a slide deck. The result is only in a slide deck, but someone saw that like for margin losses, if you do a particular manipulation, the bias remains unchanged. And like I was never, like we actually cite the slide deck instead because that's the best we could do. But yes, there is a connection and like people have kind of like run into the same behaviors. But as far as I'm aware, at least it has always been for like very specific edge cases as opposed to a general result. But 100%.
I don't know what I'm saying. I have for a very long time been looking at problems, and I always see, you use the word marginal also, I always see that somehow the global thing is defined in one space, and the marginals are defined in the other space. And it's just always, so like somehow Ensemble, you could see it as, you know, an instantiation of the thing that you're trying to estimate, and you estimate it in different ways. Like, and it's actually also here in Wainwright Jordan, I don't know if anybody knows about marginal polytope, or like iterative proportional fitting, somebody used that word at some point. Like where you have margins and you want to estimate the joint from it. You always iterate, and I think Arindam is not here, but he has it in his paper on the KL, the Bregman thing, where he tries to write EM algorithm in this way. I don't know how to put these things together, but I've been thinking about parameterizations. These certain parameterizations are better in putting things together, and that happens in one space, and the other parameterization are better for observing, and that happens in the dual space. I don't know how to put this, but maybe somebody who knows math better than me, somebody write something better here.
Well, I definitely wouldn't say I'm not better than you. However, I mean, at least, I guess for over time, I can just talk about you. Talk about this with you later.
Okay.
But I have.
Yeah, that's just a comment.
Yeah.
Sorry, it was not.
Any further questions? Okay, let's thank Zelda again.
All right, thanks so much for the intro. And honored to be here for the last talk of the last day. Thank you. MT assured me it had nothing to do with the topic, which is related to LLMs a little bit, not so much. But the title is actually not so good. Initially, I was planning to present some other stuff, but I mean, you'll see. I don't have to spoil it. But it's joint work with Rohan Anil, Christopher 50, who's currently in Stanford, and Manfred Warmuth, who's my PhD advisor. So anyway, start with a disclaimer. So this talk is by no means an extensive study. I'm fairly new to the field, so this is basically based on my experience in the past year and a half working on Gemini. And there are some stuff that unfortunately we don't publish, but I have some basically more or less like techniques that we have published before, so I guess those are fine. And yeah, so this is my personal take on understanding representation and quote-unquote memory in transformers. So I don't know if memory is the right term to use here, but you can always think about it as representation. Let's say just ignore the word memory. And yeah, I would appreciate any feedback and references if you know related work. Yeah, please let me know. So as an overview, so I was basically I decided to basically start going through one of the models that are very popular these days, transformers. You hear about LLMs. I'm here to take the heat. So basically going through the LLM, transformer architecture and the building blocks of that. And basically my understanding of how the representation is kind of like transformed throughout the layer. And bridging that basically understanding with a completely different problem, which is knowledge distillation. You have heard it throughout the talks. And how we can use that kind of intuition to build different techniques for knowledge distillation. And then finally some concluding remarks. So anyways, so transformers, right? Most of you might have seen the models already. They were introduced by Vaswani et al. In 2017. They are kind of like the state-of-the-art models for large language models, display architecture, basically. Initially, it was proposed as an encoder-decoder model, meaning that you're translating from a language A into language B. So the encoder's job is that basically takes the sentence in the source language, it encodes it into a sequence of, let's say, representations. And then the decoder's job is it kind of like cross-attends. I will show you what that means. or attention at least, self-attention, on that sequence, and also the sequence that has the model has generated so far, and basically produces output, right, iteratively. It's an autoregressive model, essentially. But these days, we mostly use decoder-only models because we are using it for generative, as a generative model. So you start from like a start token, and you just keep recursively producing output. You might have some context for that. You have like a query from the user, or you have like some document you pass as like the context, and the language model based on that context starts producing the output, right? Mainly I'm going to focus on the building blocks in transformers. I would say there are three main building blocks, components. One is the embedding layer, which is, it's in the very bottom. It's called input embedding and output embedding. So you can call both of them input embedding in this case. And then there's also a softmax layer at the output here, which typically it's shared. So these are coupled parameters. So you have an embedding table at the input. So the size of that table is your vocabulary size times number of dimensions of the model. And so at the output, you have the exact same matrix because you want to basically produce class probabilities, right? So you do basically you get the representation inner product by each row of that matrix, and that gives you logits, right? So they have two different purposes. In the input, I'll show you what it does. At the output, you can think about it as a softmax layer, basically, like for classification. And then we have multi-head attention and feed-forward layers, right? Which is basically, if you consider the model, initially, at the very first layer, you do an input embedding lookup, which I'll show what it means. And then you have these blocks of transformer blocks, we call it, which is multi-head attention and feed-forward layers, repeated n times. So on top of each other, basically. So you have this block, and then it processes the input and outputs it and passes it to the next block, right? And notice that it's a residual model. Basically, the input to the block always passes through. So it goes here, it goes to the multi-head attention, and then there's like a branch that is kind of the residual, and they get added. You have layer norm and whatnot, you can ignore those for now. But it's always residual, so the dimension of the model, like the representation, is going to remain the same throughout, right? You can ignore the multi part for now in this talk. Those are not so important. But let's say the input embedding, right? So you know we're working with, usually we're working with text. And the text, you have to kind of like find a way of breaking it down into so-called tokens. We call it tokenization. What it means is that let's say in the early days, we had basically word-level tokenization. So we would take a vocabulary for English language, and then break down our text. In this case, it is hello world and an exclamation mark. So we break it down into three tokens. It's hello world and basically that exclamation mark, and then in any order, you can assign unique IDs for these, right? So let's say you have 250,000 words, vocabulary, you assign a unique number, right? And then, so how do we use this? So input embedding, so you have tokenized your input, and the goal is that for any word or any token, which is, now we use like word pieces, you want to basically learn the representation. This is similar to like word-to-vec you might have seen. So you want to map the words in some latent space such that there's like semantic meaning between the words and whatnot, right? So in the very first layer, we tokenize, and now we just have a sequence of tokens, and we want to basically look up the corresponding representation to pass as the input to the model, right? So you might think of this operation as, let's say I have the exclamation mark, and then that is mapped to token ID 999. So you have a very tall matrix, which is 250,000, let's say, vocabulary size, times model dimension, and you're looking up the corresponding row in that matrix, right? So that is the operation that we are doing. We're basically picking one row. But another way of looking at it is that you have a weight vector, which is one hot, it's all zeros except one, at the corresponding, basically, token ID, right? So if you look at it this way, I would like to propose that this is sort of a weighted combination of the rows, where the weights are kind of like, in this case, it's trivial. It's like a one-hot vector, right? But this kind of like way of looking at things is going to become useful. So bear this in mind. Now we go to the feed-forward layer. So remember we had the input embedding, and then we have like these blocks of attention and feed-forward. I'm going to start with feed-forward because it is more relevant to input embedding. So in the input embedding, remember, so we have a fixed representation for the words or tokens, right? So each row, although it is like trainable, once we train it is fixed, right? So now, what does a feed-forward block do? And by the way, if you have questions, yeah, go ahead.
Yeah. It's just everything is trained at the same time.
Yes, this is trained, so yeah. But ignoring the train time, after training it is fixed, right? So that was my point. Basically, once you train, now you have representation for words and tokens. So now, a feed-forward layer is technically an MLP. It evolved over time. Initially, it was like 2 basically matmals. Now we have like 3. We have like, basically the input comes in. Remember, we have the input dimension, let's say it is like 1000. So it is d-dimensional. What it does is that basically it goes through 2 matrices. So these matrices basically expand the input. So you go from dimension d to around like 4d to 8d, right? But this expansion is going to be important for the purpose of this talk. So you do an expansion. Now you have 2 vectors here. And you have it for each vector in the sequence of the basically tokens that you have. The bottom one, which we call gate, FFN gate, it has a nonlinearity that is minor. Basically, it kind of zeroes out some of the values, and then this get element-wise product by each other. And then that goes through a second FFN, call it FFN2. By second, I mean FFN1, FFN2, we call it gate, right? So FFN2, it does the opposite operation. It basically shrinks. And remember, I told you this is a residual architecture, so the dimension should remain constant, right? So it goes from 8D, let's say, to D, right? So why did I bring this up? Because, again, if you think about it, this FFN2 is a tall matrix, right? And what this mechanism is doing is essentially it's finding some weights for linearly combining the rows of the FFN2, right? So if you recall, we did this in the very first layer. Now we are repeating this here in the intermediate layers. If you, maybe like those who are familiar with like older methods like LDA, we had some similar concepts, right? We break down a document into like a linear combination of topics, in a sense. And this is kind of similar to what is happening in that case, right? Now in the intermediate layers, we don't have like a unique representation for a concept. That could be like infinitely many concepts, but probably we can construct more sophisticated concepts by doing a linear combination of the rows, right?
It's the increasing of the dimension that's weird, right?
Yes, why is it? Exactly, so essentially you can think about that hidden dimension, which is like the first dimension in this matrix, as your vocabulary size, right? So there is some trade-off, and I mean, usually if you go below 4D, 4 times D, it like degrades the quality. And if you go too wide for other reasons, for optimization reasons, it doesn't work well. But essentially that is critical to have like an expansion. And I believe this is what is happening. So and again, remember in this case, the table is again fixed. Your embedding table is fixed, right? Yes, question?
Is there so you wrote Gelu separately.
Yeah.
Does it mean that the rest of the networks are just linear?
They are linear, yes.
And no non-linearity?
No non-linearity in this case, yeah. Usually, I mean, there are other variants, but in this case, yeah, this is just only a, this is what is common, basically. We call it gated Gelu, essentially. Okay, hopefully I've convinced you so far. There are 2 components that are doing something similar. They're doing an embedding lookup of a tall table. So now we have the attention mechanism. It's like it looks very different than these 2 components, right? So what does attention do? So attention is essentially, since you have a sequence, right? So the sequence gets mapped into values. In the very first layer, it gets mapped into, basically, you do an embedding lookup, each token gets mapped into its corresponding representation of that word, right? So the sentence here is that see that girl run, and each of these have a unique representation in the very first layer. And as it passes through the network, so for every token, you have to decide the new representation that you're creating for that, how important the remaining tokens are in the sequence, right? A good example is that, let's say you have a sentence that you have generated so far, the capital of France is, and then you're trying to predict the next token. So I would say the more important words in that sequence to look at are the capital and France, right? France. So you basically, essentially you need that information that, you need to know where to look, basically, because not all tokens are equally relevant for every token in the sequence, right? So that is why we have this attention mechanism. It essentially, what it does is it gives you a distribution for each token. It gives you a distribution over all the tokens to basically create a new representation in terms of like how important those tokens are, if you think about it. I don't know if I did a good job of explaining this, but okay, so maybe after I finish this part. So let's say in this case we have the sequence. So what we do is we create three different intermediate representations. We call them query, key, and value, right? So each of these are a matrix multiplication by of the current represent. So basically you multiply the sequence of vectors that you have, each of those by a matrix. You have three matrices, WQ, query, key, vector. So for each token, which is each of the tokens are query, so you're querying basically which remaining tokens are essentially relevant. What you do is you do an inner product of the keys, right? And those are your, essentially those are your logits. And then after doing the inner product, you take the softmax of that. You see the equation on the right, basically. You take the softmax of that. There's a scaling, which is 1 over square root of d, which is the inner product dimension. And now, once you have those softmax probabilities, you basically combine the representation of all the tokens to create a new representation, right? Based on these v values. But if I now write this in a different way, slightly different way, now again you see that this is something very similar that we had before. So the v matrix in this case is our embedding matrix, and then the coefficients here are now the softmax probabilities, right? You might think that, okay, the previous ones were linear combinations. Why is this a probability distribution? Doesn't even, I don't know, I just leave it to you if you have any thoughts. I have my own conjecture why it is softmax. Okay, I'm just gonna give you the answer, maybe like my understanding is because the sequence length changes over time, right? So if your sequence is too long or too short, there's a scale problem, right? If you're combining many values or like only a few values. The nice thing about softmax is that it gives you always a unit mass. So the scale is kind of like invariant, whether you are in the beginning of the sentence or at the end of the sentence. So that is one of the reasons I think softmax is important. Yes?
Why not some normalization there?
You could, yeah, you could. I guess I would say softmax was initially used, and now each of those components are so co-evolved fit together. You could use, people have tried like ReLU without normalization or normalized ReLU and so on. Other things work, but usually there's a quality hit. Yes?
Basically, I want to say so it doesn't work as well, and I think to me the reason it has something to do with signal propagation. So softmax basically induces some kind of sparsity that helps you to do predictor 7, like helps you to learn. It has a downside as well because of that, but it definitely helps you early on. So I think there's some learning dynamics involved there.
Thank you. Yeah, there are many, I feel like people have thought about this a lot, and there are many interpretations why softmax.
So in here, the WQ, WK, and the WB are the learnable parameters.
They're learnable, they're all learnable. Okay, very good point, those are learnable, but once they're trained, what I wanted to point out that in the previous two operations, which were like input embedding and FFN, the table that we're looking up is fixed after training, right? But notice that here, the table is input dependent. So whatever you have generated so far, the table, the V table that you have, the value table that you're kind of like doing a complex combination, that depends on the input. So in a sense, you can, does that answer your question? I mean, your question was about trainability. Yes, all of these are trainable parameters. Yes, these are.
My question was about that actually, this attention.
Mm-hmm.
So in training that, you train WQ and WK as separate matrices.
Yes, very good point. So, I guess, yeah, people ask that question, why don't you combine them into a single matrix? People have different answers. To me, Manfred and I, during my PhD, we did some sort of like gradient descent analysis on like factored form of matrices. So we have like that, what we call a spindly matrix. So it's like a U times V, you have, your weights are split into two, they're like a Hadamard product of each other. And in the matrix case, you also get a very different dynamic. You get like spectrally sparse solutions. And I feel like it has something to do. It gives you a very different dynamic than combining them into a single matrix. That's a very good point, yeah.
So it has the same.
It has similar properties, right? So you instead of training one matrix, you're training a product of two matrices with gradient descent. At that dynamic, like the continuous time dynamic is very different than doing gradient descent on a single. Oh, it's almost like exponentiated gradients.
And is that also what you do in the feed-forward layers? Is the feed-forward layer a single matrix, or is it like a product of matrices?
No, these are single matrices. These are a separate matrix, and this is like the Hadamard product here is at the outputs, not on the weights, basically. So yeah, that's slightly different. Yeah, very good point. Thanks. Okay, so question, yeah, go ahead.
Sorry, maybe just because you're talking about this, and this reminds me of this Metaformer work. I don't know if you heard of this. So what they're saying is like, actually, you can just like grab the transformer, like the whole architecture you just showed before, but then they are saying that this attention is actually not that important. You can just like remove it and then replace with a very daunting like average flip or like random stuff, and then it still works quite well. And I don't know like how important we should actually be looking into like this attention.
Very good point. I don't have the that's one of like the alchemy part of this, right? So actually there's a blog post by Ophir Press that so the order also doesn't matter that much. So it's not like, you have to put like attention, FFN. You could put a bunch of self-attention, like one after each other, and then put FFNs. There are also like other architectures like parallel blocks. They are kind of like, you have a residual, and then each of these are done in parallel, and you combine. And I've also seen like attention on the like transformer, the opposite. So there are many variants, but I mean, my point is mostly about principle of what is happening, and I feel like attention and FFN are doing slightly different things because FFN is so if you think about like by memory, what I'm saying is that sometimes you ask these models a question and it kind of can memorize the answer, right? You can say like the president of the United States is, and it can give you the output. And I feel like if that is being stored somewhere, my guess is that it's most likely in the FFN, because this is where you have like the basically representations, and you just the model learns how to look up that information. Whereas this is attention is more like contextual memory, that you basically pass a query, or like you have like you pass a document and you attend on that, and you know where to look in that document, right?
I just had a quick remark, which is I worked a lot on like alternatives of softmax, like essential stuff. So I have a lot of thoughts between these things, and they're not qualitatively the same. I'm happy to talk afterwards if anyone is interested.
I'm glad you're here. Actually, as I said, I mean, as a disclaimer, I don't know all the work, not even close. And people have done a lot of work like on different alternatives. So, questions or should I? Okay. So to recap, basically I showed you three mechanisms, and my point is that they're kind of like all the same principle, right? So you have some sort of, you create or you have a fixed embedding table, and then you do a linear combination or a convex combination of those representations. So the representation kind of happens as like a combining a set of like base representations and whatnot. right? So this was kind of like the base idea that I wanted to show. And yeah, as I said, some of them are fixed representations, some of them are input representations. So initially I was gonna basically go into like historically how people viewed this and like how they wanted to add more memory. So this is, for example, a paper that is 2015. This predates attention, and they did something very similar to attention. So I feel like this has evolved over years very gradually. So they had like similar ideas back then. Another work, basically, they implicitly add memory tokens to kind of improve the memory of the model. So these are the tokens that quote unquote, they basically encapsulate like contextual, long context information and so on. There is work by a couple of Googlers. It is adding extra memory to transformers. This is like a sketch-based memory that you do a sparse memory lookup. And the principle is the same. Again, you see there's a table here. You just do a sparse memory lookup. There is N-grammar, which is, I think it's a really cool idea. It hasn't been appreciated as much. I'm not a co-author, by the way. I thought the engineering part was interesting. So what they do is, so the general idea is that we have like unigram representations, right? Why don't we use like bigram representations? And you might think that, okay, this like things kind of get mixed up in between, right? When you do attention, you kind of mix all the tokens. So there's no like unique unigram representation after the first layer. But turns out this actually is useful, especially if you add it at the very first layer. So in order to form representations for bigrams, you know that's quadratic, that's too large. What they do is they do clustering and hashing, basically. So they cluster the token representations, and then that's still large, so you hash basically a pair of cluster indices. Anyway, so these are very cool ideas, but that's not the, basically that wasn't the topic of my talk. So I wanted to basically show how we can use this in a very different context, which is knowledge distillation, right? So there were many great talks in this workshop. I'm kind of feeling that I'm repeating here. So there's knowledge, you know the general idea in knowledge distillation. So you have a large model that is trained, and you want to use the information representation in the large model to improve the training of the smaller model, which we call the student. So it's a teacher-student training. The original technique is done by Hinton et al. In 2014. There are many other variants. They kind of like try to do representation matching in the intermediate layers and whatnot. But so I just want to broadly talk about the principle here. If you think about all these techniques, you don't usually increase the number of parameters of the student in these techniques. So you just don't add anything in terms of capacity of the student, and you also don't add anything to the data. So the data is exactly the same. What you add is essentially, we had that discussion about the uncertainty of the teacher, and I feel like the information kind of comes from that, right? So you know, like the teacher's representation in a sense, like what kind of decision boundary it learns, and then the student can kind of like, by mimicking that, kind of like learn a better representation eventually, right? But so there's no information about the intermediate representation of the teacher, at least in the classical knowledge distillation, which is like a soft-label distillation, right? So you let the student kind of figure out its own representation, whatever it is. It's probably in a lower dimension because it's a smaller model. But there are several problems here. For example, if the teacher is too large, you might expect that because of the complexity class of the model, the teacher is learning a much sophisticated decision boundary, and the smaller student might not be actually able to replicate that, right? So those are all plausible concerns. But what we kind of came up with, this is like a while back, we did this, so like a year and a half ago maybe, which is, what if we are allowed to add some extra parameters to the student? This is fine, but how could we use those extra parameters? Like, what is the smart way of kind of like adding more weights to the student, but kind of like using them in a nice way? And basically the whole idea is here in this basically graph. So you have a trained teacher network. Let's say you pass input xi through the teacher. It transforms it into like an intermediate representation, right? So slice the teacher at layer L, the representation at layer L is YIL, right, for input xi. And now, what if we did the following? What if we found a way of approximating YIL by y hat L by a kind of like a linear combination of, I'll show you exactly how, but like by simpler way for the student. And then once you approximate that representation, you can pass it throughout the rest of the network, the teacher network, right? And if the approximation is good, you can basically replicate the teacher's output, right? But the advantage here, we want to utilize it that y hat L is like a linear combination of a bunch of base vectors, right? Like principal directions, you call them, maybe. So we have like a vectors v1, v2, v3 in this case, plus an m, which is like a bias vector. And those are learned from the teacher directly. So, right, let's learn those from the teacher. And this representation is not that it is large, right? It's like 8,000, let's say, dimensional if you have like a CFAR. So these vectors are basically long vectors. These are 8,000 dimensional. But the student is only predicting, let's say, 3 numbers here in this graph, right? So the problem for the student is much simpler, hopefully, because if you learn these vectors in a nice way, they're kind of like well-behaved, the student's problem is a much lower dimensional problem, so it can basically generate, like replicate the teacher much easier, right? And for the rest of the network, you can technically repeat this process, right? You can just basically take this as the input and cascade the same technique, right? So you can have a student that basically mimics or like approximates the rest of the representation of the teacher, right? Yeah, okay, so very good point. So basically you add a bias vector to a linear combination of v1, v2, v3 by coefficients coming from the student. But, very good point, there's a nonlinearity usually, right? So these are in the pre-activation domain, and then you apply the nonlinearity, FL. Yeah, I almost forgot that. So the linear combination we do is in the pre-activation, and then we apply the whatever activation function that we have in that layer, FL, to form the post-activation, so-called, right? So this might look very familiar to you, right? This is very similar to PCA. You want to write the input, sorry for the mixing notation, so here is X. So you want to represent X as a linear combination of a bunch of principal directions plus a mean, which is M. And this is a very well-known problem. So the constraint is that your V's are on the Stiefel manifold. These are like, you want to have like a low rank representation essentially. So if you have D dimension, you have K components, K is less than D. And so V lies on this manifold of orthonormal K-frames, which is U transpose U is identity matrix. So the inner product between any of those directions is either 0 if they are different or 1 if they are the same, right? But notice that we have a nonlinearity here. So it makes sense to kind of like use a nonlinear version of PCA, right? So we came, okay, before that, Bregman divergences, again, it's a repeat. Zelda covered it nicely. So you know what it is. So it's if you have a strictly convex differentiable function, you can generate these divergences, which are very common in machine learning, squared Euclidean and relative entropy, Borg, and like so on, beta divergences. And the nice thing about many nice properties, but one of them is the derivative, which is, notice that I'm here using the little g. Always, if you have a convex function, it's capital. If the derivative function is what we call link function, it is the lowercase. And the derivative with respect to the first argument is the difference between the links applied to the first minus second argument, right? And again, my graph is much uglier, I would say, like this. This is what Manfred generated in the 90s. I don't know, I guess the renderings back then were so good, and I took it from his slides. I never tried to fix this, but yeah, this is like a nice smooth function. Hopefully it's too far so you can see this. And yeah, so this is the gap, right? So Zelda covered this. But now, okay, how is this related to the nonlinearity, right? So again, this is the idea of a matching loss. So if you have a nonlinearity in the network, let's say leaky ReLU, soft class, I don't know, tanish, and so on, we can actually utilize that nonlinearity to construct Bregman divergences. So the way we do it is that we call this matching loss. Manfred discovered this many years ago, but there are other, I guess, proper composite losses are, Bob Williamson and so on. So people have discovered it in different contexts. But the idea is that, let's say you have a strictly monotonically increasing nonlinearity, right? And you have a model that predicts a pre-activation, and you pass it through that nonlinearity to predict your output, right? So the pre-domain is A and A hat, and post-activation is Y and Y hat, right? So now let's say your target is Y, and your model is predicting A hat, which you apply the nonlinearity to predict Y hat, right? So one way of generating a loss function is the following. So since you have a strictly monotonic function, if you have Y, which is your post-activation target, you can always pass it through the inverse function and find A, which is the corresponding pre-activation for that target, right? So this is clear from the plot. And then now define this loss, which is the integral of the graph of the function minus the graph of the function at A. So f of z minus f of A, so it's basically this light gray area. And this I learned from Frank, that if you look at the other side, it's actually the dual function, so it's nice. So I included in my new plot. So anyway, so if you look at this area under the curve of the function, that's always non-negative because you have a strictly increasing function. And it's in fact a Bregman divergence. The nice thing is that although your argument is A hat, the overall loss is always convex in A hat, right? So why is this nice? Because let's say you have network, whatever, whichever network you're using, or like a logistic regression, you predict your logits, you apply softmax, and then you apply the KL divergence. The order is important, so you're doing the KL of the label, comma prediction. So your prediction is nonlinear in your weights, in the output weights, right? But because of this duality of Bregman divergences, your pre-activation, which is A hat, your logits, is a linear function of your weights. And since you have convexity with respect to pre-activations, you're in fact convex in your weights, right? So this comes free for matching losses. So although it looks like very convoluted, but you have convexity always, right? And the derivative is again nice because it's a Bregman divergences. Okay, so now again, why do we do all of this stuff? I'll give you one good example. So you can do this for many nonlinearities that you see. And okay, so I'll get into that later maybe. But let's say ReLU and tanh. So ReLU is, again, it's not strictly monotonic. Think about it as leaky ReLU. So let's say if we have basically a loss that we want to define between a target, which is output of a ReLU layer, and what the model is predicting, right? So if my pre-activation, if my target is, let's say, something positive, sorry. If I want to predict something positive, ReLU on the right side is linear, right? So I have to predict something positive, right? So it makes sense that to punish for that mismatch. So if the model is saying, if the label is saying 10 and my model is predicting 5, so I can say that maybe like 10 minus 5 squared is my loss, right? But if my pre-activation target is something negative, and what my model is predicting is something negative, it doesn't really matter what my model is predicting, right? Exactly, because after applying ReLU, it's all 0, right? So there's no point in punishing the model for predicting something negative that has mismatched with the label, right? So this is like an intuition that I wanted you to have, that this kind of like takes into account the nonlinearity. The other way of thinking about it is that, for example, tanh kind of like saturates beyond certain points. So if you look at the pre-activation domain, it doesn't matter if you're predicting 10 or 15, they're pretty close in terms of post-activation, right? So there's no point in punishing. And you can do this for a lot of activation functions that you see. This is a list. And then you might ask, oh, we have GELU or like Swish, what do we do with those? Yes, of course, they are not strictly monotonic, but there are ways that there are tricks you can use. For example, you can calculate the integral of GELU, you get something non-convex, but you do like the Fenchel biconjugate. Sorry, question? Yes. Yeah. So there are tricks you can use in practice. You can do differential by conjugate and get a nice convex function, and then maybe you use that as the, that's not the only way, but yeah, like one of the ways you can handle those kind of activations.
So is this the reason, like the limit function is different, so it's different from this exponential family PCA? Collins 2002?
Yes, yes. I mean, there are other PCA variants. We are kind of like essentially all of them are doing the same thing. We did it like more rigorously. I'll show you like a few other components that we added. You can add a mean, and the orthonormality constraint is slightly different. But yeah, they're all kind of like similar approaches. Like exponential family PCA is one of them. Yes, like essentially instead of Gaussian, you have like a general exponential family, and you have Bregman divergences.
Yeah, because like when you said Bregman, I thought for every convex function there is exponential family, it should all cover it, is what I thought.
Right.
So then I was wondering what is different.
I guess
not,
maybe.
Not to shit on your work.
No, not at all. Not at all. So basically, it's several things, right, in this work. Basically, we are saying that, okay, let's create this essentially table that we need to do linear combination. How do we learn the table? We can use a Bregman divergence loss. You can think about it as the PCA problem, and then how do we solve it, and so on, right? It's very similar to previous approaches. Actually, Richard Knock also has a paper on, So I guess the solvers and whatnot are kind of different. Here we use gradient descent because of the formulation. I'll show here. Okay, so this is what we write the problem as, right? Before in PCA, this was square loss. Now the difference is that you have the dual Bregman divergence. There's a reason for this, I'll mention. So you have the input and f of the linear combination, right? So notice that this is pre-activation. This has now become post-activation. This is post-activation, and then you have f star. And because of that equality that you see there, you can also flip the arguments and go to the dual, and then your first argument will be whatever is the insight because you are applying the inverse function, and that's always convex in that, right? So that's the main reason that you're using in this form, basically the dual and then the order of the arguments. And now, so we have now this problem. We have we want to learn M and V and C at the same time, and now V are what we call. We gave it a silly name. We called it Riemann-Stiefel manifold. I don't know. Frank probably knows. I don't know if it has really a name. So this is the manifold that we define as you have basically matrices U that are D by K, and then you have the Riemannian metric that gives you this matrix, basically D by D matrix, that essentially changes the inner product. So in terms of in Euclidean orthonormality, the way we think about inner product is that you element-wise multiply the vectors and then you sum them up, right? So now when you have a Riemannian metric, the cross terms appear. So the elements kind of like Ui and Vj gets multiplied together, and then the coefficients are coming from this positive definite matrix, which we call I always use the wrong term, matrix, Riemannian matrix. Apologies if it's the wrong terminology. But yeah, so you have this matrix in the middle, right? So to do things right, quote unquote, we want the orthonormality to also follow the geometry of the Bregman divergence here, right? So we have this matrix M, which is related to the second derivative of the convex generating function, right? So how do we solve this? We do couple of tricks. One is that we say, okay, let's just first solve for M, ignore V and C. So what is M? If you didn't have V and C, what would M correspond to, right? M would be like a single vector that essentially compresses your entire data. So this sum is over data points, and you can also call it a population minimizer in a sense, right? So think about in the Euclidean space, you have like a cloud of points. You want to pick one point that minimizes the loss to all the sum of the loss to all the other points, right? So it's the same thing here. You have like a population minimizer, but M is in the pre-activation domain and X is in the post-activation. So it turns out in the Euclidean case, it is easy. It's just the average. And in the Bregman case is also very similar. So you take the average of your observations and you take the inverse function. So it takes it to the pre-activation. So this is the first approximation. So if we fix mean, and now we have V and C, right? So V and C, let's just use gradient descent, right? So remember V had like a special structure, which was this orthonormality. Since we are training everything with gradient descent, these factors, you can always kind of like combine them in a sense. So you can do the optimization and do the projection at the very end. So let's say we train on V and C until convergence. Now we have a matrix V that is not orthonormal. We want to orthonormalize it. One way is you do QR decomposition, right? So if you have a matrix V that you want to make it orthonormal, you apply QR. In the Euclidean case, QR decomposition gives you two factors, Q and R. Q is orthonormal, the columns are orthonormal, and R is an upper triangular matrix, right? So turns out, very nicely, if you have a matrix M that you want to find a Q such that, so given matrix A, in this case RV, that you want to find Q that are basically the column space of that matrix, such that Q transpose MQ is equal to identity. Turns out you can do it very easily with the following trick. So take matrix A, multiplied from the left by square root of M. This is doable because M is positive definite. Apply QR decomposition, you get Q tilde on R. Now form the matrix Q by multiplying it by square root of the inverse of M, right? And the proof is very simple. It's like basically one line that gives you the right basically components. So now you have a matrix Q, and then everything else gets absorbed into R, right? So you have now everything is R. Same thing for V and C. So since we always work with V and C, now write V as a Q times R. Keep Q as your new V, and R gets multiplied by C, right? So you can always kind of like this, because everything is trained with gradient descent. And by the way, these are kind of like, the problem is convex with respect to V and C individually, but not jointly convex. It should be clear from, so it's linear, right? So if you can do, we're doing block coordinate descent essentially, and each problem is convex. So anyways, that's the long story. Experimental results, I guess. Why do we do all of this? Why did we go through all of this trouble? Turns out actually it works. I mean, you take a ResNet, let's say, you train it with leaky ReLU. That leak is very small for the theory to work. And the representation is 8,000 dimensional, just before the softmax layer. And now if you compress that representation via like regular PCA, and then increase the number of components, it's not as good as when you're doing nonlinear PCA, obviously. So you see that nonlinear PCA is always better. You have two options here because, oh, that's right.
Sorry, just a quick question. How big is M?
M?
Just looking back at the proof of how to do the QR, like you have to do the square root of M minus N.
Yeah, M is D by D, yeah, D by D matrix.
So it's like 8,000 by 8,000.
Yeah, but usually it's diagonal, right? Because, yeah, unless if there's like a softmax. Yeah, good question actually. So in this case, since we have leaky ReLU and we have like a space that is RD, we can either do PCA in pre and post, and turns out one of them is better for some reason. If you do your PCA in the pre-activation domain, it is better. Probably things are less stretched in the pre-activation because you have leaky ReLU. After that ReLU part, things get kind of clamped around 0. But always Bregman PCA is better. And then same thing for the softmax layer. You can repeat this for the same model for the softmax layer. There are other PCA variants we tried that are nonlinear. We couldn't make the optimization work. I believe it's nothing wrong with the method, but the optimization was difficult when the dimension was high. But again, yeah, the KL divergence here lowers better for our variant. And you can actually visualize these representations. So if you basically train a ResNet 18 on CFAR, you see here you have, I can't zoom unfortunately, but you have different classes at the output. And then this is trimap. You can use any dimensionality reduction method, but use trimap. Here you see like classes like dogs and cats, for example. Yeah, this is dog, I guess. This is cat, and so on. So there's some semantic similarity between classes at the output. And then you do PCA, and you see that as you increase the basically number of components, you get closer and closer to the original representation, right? And yeah, these are just again more results. You see that this is the data limited regime, which just basically looked at the problem that if you don't have enough data, which technique is better and so on. One thing I just want to briefly mention is that our procedure for training the student was two-stage. Because you have the V and C from the teacher, you have the C's, right, the coefficients, and then you want to, by the student, you want to actually predict those C's. Initially, in the pre-training phase, or pre-training I call it, like initial stage of training, we actually use the square loss between those coefficients of the teacher and the output of the student. And then once the student was trained a little bit, we did end-to-end training. So we froze the rest of the teacher network, and then we minimize the KL diver cross-entropy loss between the output labels. And that actually helped in optimization, just for practical reasons. Yes?
If I remember exactly how it looked, like you do this at every layer, do you do it sequentially, or like it's all layers in parallel?
This graph, right? We did it once, but we could technically do it as a cascade of, we could do it you could compress multiple layers into a single student, let's say.
Which layer did you pick?
We did the penultimate layer. So it's 8,000 dimensional. That was, I guess, pretty much it about the techniques. I mean, it is better, I guess. So mainly I guess we have almost time. So my conclusion was, I believe we are still at the very early stage of understanding these models, how the representation is formed and whatnot. And memory, how these models memorize stuff. So one question is that, can we augment these models with some sort of dynamic or selective memory? If you think about like humans, when you're watching something or like reading an article, you jot down information. You don't have to memorize everything, you just memorize important stuff, right? And then you exactly know where to look, essentially, when you are trying to recall. So we need some sort of, I know people have tried this, but I'm just saying like out loud that my thoughts, that we need that some sort of selective and dynamic memory. Another thing I think is going to be important personally is a mapping between different state spaces. So currently we tokenize everything, we have a state space in every layer that kind of like gets passed throughout the layers, and we generate, right? So this state space is purely on text. Now imagine you're answering, your LLM is answering a math question that's about like geometry, right? What if we add something like a mapping from the state space, which is text, to a state space that's more like RD, right? Euclidean space or some other space. That the way we think about stuff, right, in our head, that we kind of imagine, like we kind of like think about points and lines and so on, and then we answer the question. So if you have those sorts of state space mapping, I think that's going to be good for reasoning or like question answering and so on. So I don't think we can answer everything in like a single state space. And the last thing is that, how can we do better knowledge distillation? We just did something very simple. There are obviously many other ways that we haven't figured out, but that's pretty much it. Thank you so much.
I think we have more than 5 minutes for questions.
Very well. Thanks for all that description, because I think even though I've seen that diagram, like the attention on so many times, I still don't understand it. And it's weird. Output is an input too. So anyway, I've avoided working in like understanding representation and memory in like layers or going inside and the kind of thing that you're doing right now. I've avoided that because I kind of feel like a lot of it is arbitrary. So we were discussing, right? I understand that maybe at a bigger level, some things are happening. But if you actually really, so that's why I really shouldn't use the word hate, but I used it.
It's okay, I'm here to take the heat.
The mechanistic approach, because trying to split the problem in small blocks, it's good, I guess, but then it gets like, trying to study a single neuron kind of thing, which has benefits. Right? But, so, do you have any opinions on this, on how to go about it?
kind of scared to express my opinion, so no. But, no, I'm just kidding. Scared of the community sitting here. But no, I mean, mainly my point in this talk was kind of like make people think about how these representations are formed, because it's not very irrelevant to the things that we did in the past, right? Like, not myself, but like all the, like David Bly, I guess, and other people, they did like LDA type of stuff. So there might be better ways of, you're absolutely right. I mean, we're just doing arbitrary stuff, but it's based on kind of like these linearly combining representations. So I don't know what exactly the answer is to your question, or like I don't have good intuition.
How should one go about understanding memory?
Yeah. I mean, this was basically my take, and I don't think it's necessarily correct, but it's kind of like one way of thinking about it. And I guess once we kind of have a better understanding, we could come up with better memory mechanism. I mean, why do we do like linear combination of? There must be better ways. That's all I'm saying. Yeah.
So I had a much more pragmatic question, which is like, have you thought about using this in a kind of co-distillation scenario for compression? Because to me it feels like you could, it's like an open problem of how you train like a directly a compressed model, and I can imagine sort of, I've seen lots of regimes where you train sort of together a teacher and a student to kind of make it small, but like I've never seen anyone taking the geometry of the intermediate layer seriously. It was always like an L2 or whatever. Exactly. So I wonder like whether you thought or like if you're...
Yeah, that's a very good point. This problem specifically was for a trained teacher. So you have a trained teacher, you're done with training. For co-distillation, the problem is slightly different. Maybe it's actually easier in that case because you can always train those models with gradient descent, right? End to end. So you don't have like a...
So you think adding the whole like geometric interpretation would not give you any...
Yeah. So think about it this way. Let's say if I was training these layers as part of the gradient descent, right? So I could use the end-to-end, like output as my loss, and then do backprop, right? All the way through. So I feel like this technique was specifically well suited for the model that was already trained. But yeah, that's a very good point. Yeah, I've actually was thinking about it for a while, that we could reserve some representation for the information coming from the co-distilled model, right? Like the co-teacher. Yeah, that's a very good point. Yeah.
Okay, I have one question. So, in your objective of this fragment PCA, right, that you are using this fragment divergence in the dual space.
Right.
And given that today we have heard about this new covariance features of generalized covariance features from Zelda squad, I wonder whether there's any connections, because the usual PCA can also be computed by first computing covariance matrix and then compute the leading eigenvector, right?
Yeah, that's a good point. You can show that in the squared Euclidean loss case. Basically the problem becomes an eigendirection problem. In this case, that doesn't hold necessarily because you have nonlinearity. But the reason the order is important, as I mentioned, is you can write this via the duality. You can write it as df of this component, comma f inverse of the other one. And since this goes to the part that we are interested in optimization becomes the first component, you have convexity. That's the main reason we use this order. You could use the other way, but yeah, it would not necessarily be convex in terms of the argument itself. Yeah. But yeah, good point. There are other cases that we haven't published for certain reasons. That you again get an eigenvector problem, but it's not a closed form, you have to iterate. So you just basically you do nonlinear PCA, you get an eigenvector problem, but you have to basically use the solution to compute an error and then repeat basically. So that shows up actually.
You can write it as kernel PCA and then repeat.
Okay.
The eigenvector.
So you have this sort of comment that maybe we need different state spaces
Yeah.
and all those things. And that's, I mean, what are you seeing? Like, I mean, it sounded like, if you train the models on text, then the space is still going to be in text. So does training the models purely on like mathematical formulas means that you have that space?
Yeah, good question. I don't think so. For like the example that I was trying to make, like geometry, you probably need also like the images or like coordinate system, right? So I don't think the model necessarily would figure that out. Maybe, I don't know. So this is kind of like looks kind of like black magic, right? So you don't know what's happening. But I feel like you would need a certain type of data for that, a different type of data to kind of like define that mapping. And kind of like force the model to utilize that, that state space representation. Yeah. So I don't know. I just threw it in as an idea that I've been thinking for a while, but I don't have a good solution. If I did, I wouldn't tell you. So, yeah. Yeah.
Can I add a remark on that?
Yeah, sure.
Because we're looking at something in this kind of direction. So, for example, if you're thinking about additions and you're thinking about things like that. So there are components of the network that doesn't allow you to do things properly. So for example, layer norm enforces all your embedding to leave on the sphere. And so that's not exactly the space where you'd like to do additions, because additions on the sphere, like we can think of them as rotations, but that's not what the linear layers are doing. And then basically that's the reason why you can't really have numbers in a trivial way. So the architecture itself as well, somehow constraining the space. Like one simple thing is most of the latent is on the sphere instead of Euclidean space.
Thanks for the talk. I really liked it. I was wondering, like, if it's in the same direction of what like MT was saying. So I don't recall if you were here for my talk or anything. But like I was basically also talking about something similar, right? Except for we kind of went the complete opposite of that. We said like don't care about any details, don't care about data and so on. And somehow, like, if I'm just coming from a very empirical standpoint, we reach like very similar results, right? So I'm just wondering, like, what is that telling us? Like, there seems to be so many different ways of how to do knowledge distillation, and all of them kind of get us to a kind of good place. So what is it like really about in your opinion?
Well, the only difference here that I see is there's certain problems, and like so I started with like soft label distillation, right? So that is kind of like you let the student figure out what's doing. And there has been a couple of work, I guess you're aware of, pretty sure, that they try to match the representation, but then this becomes like an identifiability problem, and then dimension mismatch. They try to like kind of learn a projection matrix from the teacher's dimension or up projection from the student, and essentially. So all of these, I mean, our motivation back then was very different. We were just saying that, what if we just fix the representation and then do a simpler problem for the student? I don't think this is the best way, honestly. So I've had many thoughts since then, but this was kind of like the prototype of trying to get rid of that, especially the identifiability problem. That's kind of like, you can just, like have different representations, and like how do you make sure that they are matched and so on. So yeah, I mean, that's a good question, and I don't think this is the best technique for distillation. This is just the alternate way of thinking.
Yeah, just like this wasn't a critique, right? Like I also
of
think
course,
our technique is the best knowledge.
It's a very broad problem. There's so many unknowns. As I said, one was about the representation of there's like some misconceptions about distillation that, if you have like a very good teacher, you always get a better model. But that's not necessarily true empirically, at least what we have observed. And then there's so many other issues with the loss that you use. Why do you use KL? I mean, I don't know. You can use reverse KL. That's kind of like zero forcing, for example, property. Is that good? Sometimes. So yeah, there's so many unknowns, and yeah, thanks for bringing it up. I mean, I feel like it's like a very, at least to me, it's like a very early, like science, like this distillation, like a young science.
Okay, maybe let's thank Ehsan again.
Yeah, thank you.